Every once in a while, something unusual enters our solar system, something that didn't form here. Recently, astronomers discovered a new object named 3I Atlas, the third confirmed interstellar object ever found passing through our solar system. Unlike asteroids or comets that orbit the Sun, this object came from beyond, most likely from another star system. What is it made of? Where did it come from? And could it carry clues about how planets and life form in distant corners of the galaxy? What do we know so far about 3I Atlas? Before we delve into all the details, comment below where in the world you're watching from and subscribe to our channel to help our community grow. A mysterious visitor from far beyond our solar system has quietly entered the vast space that surrounds our Sun. This new arrival is called 3I Atlas, and it is unlike any other object we usually see in our skies. It is only the third confirmed interstellar object ever observed, an extremely rare traveller that began its long journey around another star many millions of years before our own Sun even existed. Its name itself tells a story, symbolising both where it came from and its short visit through our part of the cosmos. Unlike the asteroids and comets that orbit the Sun again and again, 3I Atlas is not here to stay. It is on a one-time hyperbolic path, meaning that after passing through our solar system, it will continue outward and never return. Because its visit is brief, scientists have only a short time to observe it, but that short time offers an incredible opportunity to study material that formed in another star system. 3I Atlas has not been shaped by the same conditions that built our planets and comets. It is something truly alien, a small piece of a distant world that has wandered across the galaxy to cross our path. Its name, 3I Atlas, reveals how special it is. The word 3 shows that it is the third confirmed interstellar visitor ever detected, after 1I Oumuamua, found in the year 2017, and 2I Borisov, discovered in the year 2019. The letter I means interstellar, a symbol used only for objects proven to have come from beyond the Sun's influence. Finally, Atlas honours the telescope system that first spotted it, the Asteroid Terrestrial Impact Last Alert System, or ATLAS. This system was designed to search for asteroids that might come close to Earth, but in doing so, it has also helped astronomers find visitors from other star systems. The discovery of 3I Atlas quickly excited astronomers around the world. On December 12, 2019, the ATLAS telescopes in Hawaii detected a small, faint light, moving rapidly against the background of stars. At first, it seemed like just another comet, a blurry spot with a gentle glow. But further studies revealed something extraordinary. Its orbit was not a regular loop around the Sun like normal comets. Instead, its path was hyperbolic, meaning it was moving too fast to be captured by the Sun's gravity. When scientists traced its movement backward, they confirmed that this object had come from interstellar space, just like Oumuamua and Borisov before it. Detecting such an object is an enormous challenge. Interstellar visitors are tiny, dark, and travel at incredible speeds, which makes them extremely hard to notice. The fact that Atlas was able to find 3I Atlas shows how advanced modern sky surveys have become. Each night, Atlas scans large parts of the sky, looking for objects that move differently from the stars. 3I Atlas immediately caught attention, not only for its speed but also for its unusual direction. Once astronomers realized its true nature, telescopes across the world began to study it closely. Every bit of data mattered: its brightness, its color, its shape, and even how it rotated. Early observations revealed that 3I Atlas was active, forming a faint halo of dust and gas as it neared the Sun. This made it different from Oumuamua, which showed no such activity, and more like Borisov, though it appeared much dimmer. Fortunately, this interstellar visitor was found before it reached its closest point to the Sun, called its perihelion, giving scientists a rare chance to study almost its entire journey. They watched as it grew brighter while approaching the Sun, reached its peak brightness around late December of 2019, and slowly faded as it moved away again. Although it was never visible to the naked eye, medium-sized telescopes were able to collect valuable spectroscopic data. By early 2020, 3I Atlas was already dimming and speeding back toward deep space, never to return. These brief visits matter greatly to science. Interstellar objects like this stay within view for only a few months. and missing that short window means losing the chance to examine untouched material from another star system, matter that formed in a completely different environment from our own. By tracking 3I Atlas closely, scientists hope to uncover clues about its origin. It may have been ejected from its home system long ago, drifting through the emptiness of interstellar space for millions of years before finally crossing paths with our Sun. Its unusual orbit suggests that it came from a distant region of the Milky Way, but identifying its exact birthplace is difficult because of the gravitational pull of nearby stars. Still, each observation adds a new piece to the puzzle, giving us a precious glimpse of a world far beyond our reach. 3I Atlas is more than just a name in a catalogue. It represents discovery and wonder. Every part of that name carries meaning: where it was found, how it is classified, and why it stands apart from the countless comets and asteroids bound to our solar system. The most important part of its name is the single letter I. This letter tells us everything: that the object came from another star system, that it was not shaped by our Sun, and that it is a true visitor from the stars. Until the year 2017, humanity had never confirmed an object from another star system passing through ours. There was no system for naming such visitors because no one had ever seen one. That changed when Oumuamua was discovered in 2017, and astronomers realised it was moving on a hyperbolic path, never to return. The International Astronomical Union then created a new naming system with the letter I to mark these rare travellers, and so, with Oumuamua, Borisov, and now 3I Atlas, humanity has begun a new chapter in exploring not just our solar system, but the vast, mysterious spaces beyond it. The way astronomers name interstellar visitors is both simple and meaningful. It follows a numbering system that marks humanity's growing list of confirmed travellers from beyond our solar system. The first object ever detected was Oumuamua, which became known as 1I. The second was Comet Borisov, discovered in the year 2019, earning the title 2I. Now a new traveller has joined the list, 3I Atlas, making it the third confirmed interstellar object ever seen by human beings. Each new discovery continues this pattern, so the next ones will be 4I, 5I, and so on. Although these names might look like simple catalogue entries, they actually represent a growing record of mysterious visitors that have crossed the vast space between stars to reach our solar system. The second part of the name, Atlas, honours the system that first found it, the Asteroid Terrestrial Impact Last Alert System, known simply as ATLAS. This project, based in Hawaii, was designed to help protect Earth by searching for asteroids that might pose a threat. Every night, its automated telescopes scan the sky, taking images of stars and looking for anything that moves differently. In December of the year 2019, one of these telescopes noticed a faint, fast-moving spot of light. At first, it seemed like an ordinary comet, but after careful calculations, astronomers realised its orbit was hyperbolic, meaning it was not bound to the Sun at all. It had come from deep interstellar space. It is an old astronomical tradition to include the name of the discovery project in an object's official title. This helps give credit to the team that made the discovery, and it also helps trace the object's origins. In this case, Atlas not only detected 3I Atlas first, but did so early enough that scientists could make detailed observations of its brightness, speed, and composition. The name therefore became both accurate and symbolic. It honoured the system that spotted it, and the spirit of discovery that defines astronomy itself. The small letter I in its name carries enormous meaning. It tells scientists that this object does not belong to our solar system. Everything formed under the influence of the Sun, like comets, asteroids, and planets, shares a common history and composition. Interstellar objects, however, are completely different. They are like sealed time capsules from distant star systems, carrying within them ancient ice, dust, and perhaps even complex organic molecules that formed around other suns. When astronomers see that I, they immediately know they're studying something alien, something shaped under foreign conditions, where the laws of planetary formation might differ from those we know. That is why every interstellar visitor is considered so valuable. Humanity does not yet have the ability to send spacecraft to explore other star systems, but occasionally fragments from those distant systems come to us. Each visitor carries the chemical traces of its birthplace, silent messengers from other corners of the Milky Way. By studying them, scientists can learn how planets, comets, and asteroids form elsewhere, gaining insight into how common or unique our own system might be. These discoveries give us a glimpse into the greater variety of worlds that may exist across the galaxy. The naming of 3i Atlas also reminds us how young this field of study truly is. Before the year 2017, no confirmed interstellar object had ever been detected. In just a few short years since then, we have already identified 3. Though that may sound like a small number, it hints that our galaxy could be full of such travellers, silently passing through the solar system without being noticed. Earlier telescopes were simply not sensitive enough to find them. With the arrival of powerful new observatories, like the Vera Rubin Observatory and its legacy survey of space and time, astronomers expect to discover dozens, or even hundreds, more in the coming decades. For scientists, this numbering system is more than just a list. It is a timeline of human discovery. Future generations will remember 1i Oumuamua, 2i Borisov, and 3i Atlas as the first messengers from beyond the sun that humanity ever recognized. Each one marks a turning point, a sign that our understanding of the universe is expanding. 3i Atlas, therefore, is not only a name, it is a record of human progress, a symbol of our curiosity and our growing connection to the wider cosmos. Every interstellar visitor adds another piece to the story of our galaxy, carrying silent evidence of worlds far beyond our reach. Every interstellar object that enters our solar system is far more than just a frozen piece of rock or ice drifting through space. Each one carries within it a silent story, an ancient record of where it once belonged and what forces shaped its long journey. Its path through space, its speed, and its structure are like clues written in the language of the cosmos. These objects are messengers from distant worlds, bearing memories of violent beginnings, close brushes with giant planets, and the chaotic birth of stars. They are reminders of how restless and ever-changing our galaxy truly is. Among these rare travellers is 3i Atlas, an object so unusual that astronomers across the world are studying it with great urgency. It is only the 3rd confirmed interstellar visitor ever found passing through our solar system. Scientists are eager to understand it before it disappears forever into the vast darkness beyond. What fascinates them most is one haunting question. Where did it come from? If its place of origin can be discovered, or even narrowed down to a few possible regions of the Milky Way, it could reveal long-hidden secrets about our galaxy's violent and mysterious past. The first challenge for astronomers was to study its orbit. When 3i Atlas was first detected, experts quickly noticed that its path through space was nothing like those of regular comets or asteroids. Instead of moving in a closed oval-shaped orbit around the Sun, it followed a hyperbolic path, a wide, open curve that showed it was not bound to the Sun's gravity. This single fact confirmed it as an interstellar object. Comets and asteroids on elliptical paths always return, circling the Sun over and over again. But a hyperbolic orbit means something entirely different. It means this object came from the stars beyond and will soon leave, never to return. By carefully tracing its hyperbolic path backward through time, astronomers can estimate the direction from which it entered our solar system and try to reconstruct the beginning of its long voyage. Yet this is a very difficult task. Objects like 3i Atlas can drift through space for tens of millions or even billions of years. During that immense time span, many forces can slightly change their direction, such as the gentle pull of a passing star, the hidden gravity of a massive gas cloud, or even the faint attraction of a distant planet. These small influences, acting over countless ages, can completely alter a traveller's route through the galaxy. For 3i Atlas, astronomers have mapped a general incoming direction, but it points to a broad area of the night sky rather than a single star. Finding its true birthplace is nearly impossible without knowing every gravitational encounter it has ever experienced. Still, a few clues stand out. Current research suggests that it may have come from the direction of the Carina or Scorpius constellations, regions known for their enormous star-forming clouds. These cosmic nurseries are made of thick gas and dust, glowing with the light of newborn stars and planets. Many astronomers believe that interstellar objects like 3i Atlas are born in such regions. In the early stages of a solar system's life, large planets can act like slingshots, hurling smaller fragments, icy comets, rocks, and dust out into interstellar space. Some pieces may be thrown away after crashing into other bodies or passing too close to their parent star. 3. Atlas might be one of those ancient fragments. 3. Atlas might be one of those ancient fragments. Perhaps the broken piece of a long-lost exoplanet or the leftover debris from a young planetary system destroyed long ago. If that is true, its journey to our solar system may have taken tens of millions of years. Unlike the familiar comets that orbit our Sun, 3I Atlas has roamed freely across the galaxy, shaped only by the subtle forces of passing stars. Some computer simulations even suggest that it may have passed through multiple star systems before finally reaching us, each encounter slightly changing its path. These brushes with different stars could have heated its icy surface or coated it with new layers of cosmic dust, leaving behind chemical fingerprints that scientists are now eager to study. But retracing its full history is a nearly impossible challenge. Our galaxy is constantly in motion. Its stars orbit the centre, its spiral arms twist and turn, and massive clusters tug at one another with invisible threads of gravity. Trying to follow 3I Atlas backward through this ever-changing dance of stars creates enormous uncertainty. Even with today's most accurate measurements of its speed and direction, the further scientists go back in time, the blurrier the trail becomes. To understand its origin, astronomers also study what it is made of. If its surface holds ices rich in carbon monoxide or carbon dioxide, then it likely formed in the cold outer parts of its home system, much like our Kuiper belt or Oort cloud. If, instead, it contains rocky minerals, it may have formed closer to its parent star, in a warmer asteroid belt. Early studies suggest 3I Atlas is covered with easily changing ices, which means it probably came from a very cold, faraway region. Its faint glow, a thin cloud of gas and dust, shows that its centre may still hold pure, untouched material from the time of its birth. In this way, it is like a sealed time capsule, keeping the conditions of a world that may have disappeared millions of years ago. Comparing its makeup to that of earlier interstellar visitors like Oumuamua and Borisov may show whether they share the same birthplace, or if each is a traveller from a different star nursery altogether. Above all, its orbit is the clearest sign of its alien nature. Astronomers measured its orbital eccentricity, the number that describes the shape of an orbit, and found it to be far greater than 1. Anything less than 1 means a closed orbit. Exactly 1 is a parabola, and greater than 1 means open, ensuring an escape from the sun's pull. That single number alone proves 3. Atlas was born beyond our solar system. Its speed showed the same truth. Even before it came near the sun, it was already moving far faster than any comet from the Oort cloud could reach. To give perspective, comets born within our solar system, even after being pushed by giants like Jupiter or Saturn, usually move at just a few kilometers per second when far from the sun. 3. Atlas, however, rushed into our solar system at interstellar speeds, tens of kilometers per second, clear proof that it had been roaming the galaxy for ages before it ever crossed our path. As the sun pulled on it, the object sped up, only to slow again as it left. Yet even after losing that borrowed energy, its leaving speed still stayed far above the escape speed of the solar system. Simply put, it was never trapped here. Some doubters wondered whether it could have been an Oort cloud comet pushed onto an open path by a planetary meeting. But models quickly showed that such comets only ever reach orbits with eccentricities just above 1, nothing close to the extreme path of 3I Atlas. Its path leaves no room for doubt. It came from interstellar space. In many ways, its orbit is a fossil, keeping the violence of the event that once threw it out of its home system. By following its path backward, astronomers hope to guess how long it has been wandering. Current ideas suggest tens of millions of years at least, making it a survivor from the earliest days of its birth star's system. When compared with its forerunners, it shows an interesting variety. The first interstellar visitor, Comet Borisov, behaved like a normal active comet with a long tail. The second, Oumuamua, confused astronomers by spinning oddly and showing no visible tail at all. 3I Atlas seems to be a mix of the two. Its high entry speed is like that of Oumuamua, while its faint cloud reminds us of Borisov. With each new visitor, the sample grows, showing a wide range of interstellar travelers. Together they remind us that the galaxy is not empty but full of wandering messengers, each carrying pieces of stories written in distant stars. Finding exactly where 3I Atlas came from is one of the most exciting mysteries in modern astronomy. Once an object is thrown out of its home star system, it begins a long, lonely and unpredictable journey, one that can last for millions or even billions of years. During this trip, the traveller is never fully free from outside forces. The huge pull of the Milky Way slowly moves it. Passing stars tug at it as they go by, and giant unseen clouds of gas and dust cross its path, pushing and pulling it slightly. Over time, these countless space interactions twist, bend and reshape its orbit, making it almost impossible to trace back its exact birthplace. Yet astronomers are nothing if not patient. By carefully tracking the path of its open orbit, the never-ending curve that brought it into our solar system, they can at least narrow down areas of the galaxy where it might have started. When 3I Atlas was first seen, astronomers quickly worked out the direction from which it seemed to be coming. Its path pointed roughly toward the bright skies near the constellations Carina and Scorpius. These two areas are bright, active parts of the Milky Way, full of star nurseries, huge clouds of gas and dust where new stars and planets are born. Such regions are natural places for creating interstellar travelers, because during the wild early years of star formation, strong gravitational pulls can throw comets, icy pieces, or even bits of whole planets into the dark space between the stars. One strong possibility is that 3I Atlas came from a star system much like our own, circling a young, sun-like star surrounded by massive gas giants. In such systems, these giant planets move through the early disk of gas and dust, scattering smaller icy and rocky pieces in every direction. Some of these unlucky pieces are pulled into the star, others crash into bigger planets, and a few gain enough speed to escape the system completely, sent out into the galaxy as lonely travelers. Over time, these thrown-out pieces can become interstellar objects like 3I Atlas, fated to drift endlessly from one star field to another. Its chemical makeup supports this idea. The presence of water ice and carbon monoxide shows it formed in the colder outer parts of a planetary system. But there is another interesting option, a red dwarf star system. Red dwarfs are the most common type of star in the Milky Way, and many are thought to be surrounded by thick belts of icy material. These stars are smaller, cooler and dimmer than our Sun, which means their icy zones and livable areas lie much closer in. Within such systems, wandering planets or the pull of nearby stars can easily send icy bodies flying into interstellar space. The unusually high amounts of carbon monoxide found in 3I Atlas suggest it may indeed have formed in one of these colder, dimmer systems. Even so, finding a single star as its exact origin remains almost impossible. The Milky Way is always moving. Stars orbit the galactic centre at different speeds, changing their places a lot over tens of millions of years. By the time 3I Atlas reached our solar system, its original path had almost certainly been bent and turned by many gravitational pulls. Even though its path seems to point toward Carina or Scorpius, the star, or stars, that gave it the final push may no longer be anywhere near that part of the sky. Still, astronomers keep trying. Missions like Gaia, which maps the positions and movements of billions of stars with amazing accuracy, allow scientists to run computer models backward in time. These models try to find stars that may have come close to the path of 3I Atlas millions of years ago. The further back they go, however, the less clear the results become. So far, no single star has been firmly identified as its birthplace. The way in which 3I Atlas was thrown out gives more clues. Most interstellar objects are believed to be sent out during the early, most chaotic stages of planetary system formation, usually within the first 100 million years of a system's life. If 3I Atlas came from a crowded young star cluster, where nearby stars often pass close to one another, the chances of ejection would have been even higher. In such regions, close meetings with other stars can upset planetary systems, throwing comets and fragments into the galaxy at escape speed. In this case, 3I Atlas could have been sent away very early in its system's history, spending tens of millions of years drifting alone through the Milky Way before finally arriving here. Even its surface tells a story. The dark carbon-rich layer covering 3I Atlas shows an extremely long journey. Constant exposure to space rays slowly changes an object's surface chemistry. Freshly ejected bodies often have brighter, newer-looking surfaces, while those that have drifted through space for tens or hundreds of millions of years develop darker, more changed layers. This evidence shows that 3I Atlas may have been thrown out long ago, perhaps during the very first days of its home system. And then there is the most exciting question. Could it carry the building blocks of life, organic molecules, from another star system? Organic molecules are carbon-based compounds that form the base for more complex substances such as amino acids, nucleic acids, and proteins, all needed for life as we know it. If interstellar visitors like 3I Atlas carry these molecules, they may play a key role in spreading the chemistry of life across the galaxy. This idea supports a fascinating concept called panspermia, the thought that the raw materials for life can move between stars on natural carriers like comets, asteroids, and pieces of planets. In this sense, 3I Atlas might not just be a frozen traveller from another star system, but a space messenger, carrying hints of life across the vast stretch of the Milky Way. Careful study of the light reflected from 3I Atlas has given astronomers strong clues that this space traveller from another star contains complex carbon-based materials. Observers noticed a faint green glow around the comet in what's called its coma, the cloudy area of gas and dust that forms when a comet warms up as it gets closer to a star. This unusual green colour comes from molecules called cyanogen and diatomic carbon. Both are often seen in active comets, forming when sunlight breaks apart larger carbon-rich materials on the comet's surface. Beneath this glowing cloud lies a solid core, covered in layers of complex organic matter. Interestingly, similar organic molecules have been found on comets within our own solar system. These materials are believed to be the early building blocks of life, the chemical pieces that can later form amino acids and nucleobases, the basic parts that make up DNA and RNA. This makes 3I Atlas a very interesting visitor. It suggests that the same chemical steps that helped life begin on Earth might also happen in other star systems far across the galaxy. The surface of 3I Atlas is also unusually dark, reflecting very little sunlight. Its reflectivity, or albedo, which shows how much light an object bounces back, is only between 4 and 10%. This is common for comets covered in materials called tholins, reddish-brown organic solids that form when ultraviolet light and cosmic rays hit simple ices like methane and nitrogen. Over millions of years drifting through the emptiness of interstellar space, 3I Atlas would have been constantly struck by high-energy radiation. Slowly, this built up thick crusts of these organic materials. This outer layer acts as both a protective shield and a chemical record. It keeps the inner ices safe from damage while preserving the story of the comet's long journey through space. The meaning of this is very deep. If 3I Atlas, which formed around another star, developed the same kinds of carbon materials as comets in our own system, then the early chemistry of life may be a normal part of many planetary systems in the Milky Way. In young star systems, tiny ice grains coated with organics often form in the cold outer areas of protoplanetary disks, the swirling clouds of dust and gas that later form planets. Over time, these grains stick together to make comets and small rocky bodies. Later, if these objects crash into young planets, they can deliver their chemical riches, possibly helping life to begin. Even more interesting is what lies under the surface of 3I Atlas. Scientists think that its hard outer layer, shaped by billions of years of cosmic radiation, may only be a few meters thick. Beneath this thin shell, the ices could still be almost as fresh as they were when the comet first formed around its parent star. Deep inside, delicate molecules such as methanol, formaldehyde, and simple starters of amino acids might still be preserved. If humans were ever able to collect samples from this inner core, we could hold in our hands a frozen picture of the chemistry that existed in a faraway star system long before Earth even formed. This leads to a thoughtful idea. Comets like 3I Atlas are not just temporary visitors, they are messengers from other suns. As they approach stars, sunlight causes some of their ice and dust to stream into space. Tiny organic rich particles can then drift through the galaxy for millions of years until they land on a planet in another system. Experiments on Earth show that many organic molecules can survive these long space journeys if protected by ice or rock. Life itself might not survive, but the chemical seeds of life very likely can. Even the simple fact that 3I Atlas is now in our solar system says a lot. Star systems do not keep all their material. They often throw comets, fragments, and small bodies into interstellar space. There may be billions of such wandering objects moving through the Milky Way. If even a small part of them carry organic material, then the galaxy may constantly be sharing the building blocks of life between stars, raising the chances that life begins wherever the conditions are right. The journey of 3i Atlas through our solar system was not simple. Like a traveller moving through a busy market, its path was gently pulled and guided by the invisible force of gravity. The strongest of these pulls came from the giant planets, especially Jupiter and Saturn, whose huge masses had small but important effects on its path. Hyperbola, a shape that meant it was not orbiting the Sun like normal comets or asteroids, but simply passing through. Yet even a hyperbolic path can be slightly changed by gravity. The massive planets act like space steering wheels, giving passing objects small pushes or changes in direction. These small changes can teach astronomers a lot about both the object and the powerful forces at work in our part of space. Once the Atlas survey team spotted 3i Atlas, they quickly measured its speed and path. After confirming it was an interstellar visitor, astronomers began closely tracking every part of its journey, checking whether nearby planets would affect its course. Unlike comets trapped in neat oval orbits around the Sun, 3i Atlas was moving too fast to be caught. Its hyperbolic path showed clearly that this visit would be brief. Still, the pull of the solar system's giants could not be ignored. Jupiter, the largest planet, is famous for its gravitational slingshot effect. With a mass more than twice that of all the other planets combined, Jupiter can throw space rocks onto new paths, sometimes pushing them out of the solar system or sending them toward the Sun. For 3i Atlas, though, the effect was gentle. Its closest approach to the Sun was far from Jupiter, so the giant planet's pull was more of a soft nudge than a strong push. It may have slightly tilted the comet's direction, or given it a small boost in speed, but nothing like the big path changes Jupiter has caused for comets that pass closer. Saturn, the second largest planet and famous for its bright rings, may have had a slightly bigger effect. 3i Atlas's path brought it closer to Saturn than to Jupiter. Although still far away, Saturn's heavy mass let its gravity pull gently on the comet, changing its path just a little. Neither Jupiter nor Saturn could capture it, but together they may have left quiet, lasting marks on its journey. Even so, astronomers were surprised by how steady 3i Atlas's path remained. Despite the strong pull of Jupiter and Saturn, its hyperbolic course hardly changed. This proved that it was never bound to the Sun. It was a true traveller from another star, passing through a solar system whose planets were only bystanders. This story of close passes with the giant planets raises another interesting question. How many other interstellar travellers pass by without us noticing? 3i Atlas was small and faint, found only because of the sharp eyes of the Atlas survey. If such objects are common, as many astronomers think, dozens or even hundreds may be flying past us right now. Most are too dim or quiet for today's telescopes to see. Some may be thrown away by Jupiter's strong gravity. Others drift silently through the solar system, leaving no sign that they were ever here. One of the clearest signs that 3i Atlas does not belong to our solar system is the incredible speed at which it travels. Objects that are born under the Sun's influence, such as asteroids, comets, or icy fragments, rarely move fast enough to break free from the Sun's powerful gravity. Yet 3i Atlas has done exactly that. Its movement through space tells the story of a violent past. It was not slowly pushed away but forcefully thrown out from another star system, cast into the dark emptiness between stars, and left to travel for ages. This was no calm or gentle journey. 3i Atlas did not drift quietly like a floating pebble. It was launched with enormous force, far greater than anything we usually see among the comets or asteroids that circle our Sun. When astronomers first tracked its path, they found something astonishing. Even before the Sun's gravity began to pull on it, 3i Atlas was already speeding through space at around 26 to 30 kilometers every second compared with the Sun's position. To understand how fast that is, most comets from our solar system, like those that come from the faraway Oort cloud, usually travel only a few kilometers per second when they are far from the Sun. What makes 3i Atlas truly special is its hyperbolic excess velocity. This means that even after it escapes the Sun's pull, it will still keep a high speed instead of slowing down and returning. That is a clear sign that it came from somewhere beyond our solar system, a true visitor from the stars. As it moved closer to the Sun, gravity made it race even faster. At its nearest point to the Sun, a position known as perihelion, scientists estimated that it was moving at more than 60 kilometers per second. It shot through the inner solar system like a glowing streak of light before turning outward again, ready to vanish into deep space. Once it moves far enough from the Sun, it will slow slightly and return to its steady cruising speed, continuing its long, silent journey across the galaxy. But why does this high speed matter so much? The reason lies in how celestial bodies gain motion. Objects that are born inside the solar system receive their energy from the Sun's gravity. Even those faraway icy comets from the Oort cloud remain tied to the Sun, no matter how far they travel. They may take millions of years to complete one orbit, but they always come back. Their speeds increase when they pass close to the Sun, yet they never truly escape. 3I Atlas, however, is different. Its energy is far beyond anything the Sun could give. That means it must have been expelled from another star system altogether, likely during a violent event in the early days of its creation. Astronomers think that interstellar travelers like 3I Atlas are often created during the chaotic birth of planetary systems. When large planets form around a young star, they act like giant slingshots. Smaller bodies, rocks or icy fragments, that come too close can be thrown inward toward the star or outward into space at great speed, never to return. Over billions of years, these dramatic ejections fill the galaxy with lonely wanderers. 3I Atlas is one of them, a frozen relic that carries the ancient story of its lost home system within its icy heart. Its great speed also tells us how long it has likely been travelling. At 26 to 30 kilometers per second, it could take millions, or even tens of millions of years to cross the vast distances between stars. It might have been moving through space since the very beginning of its home system, possibly for billions of years. During that time, it may have passed near other stars, its path slightly changed each time by their gravity, until at last it arrived in the neighbourhood of our Sun. Compared with the other two interstellar visitors that we know of, 3I Atlas holds a special place. The first, named Oumuamua, entered our solar system at about 26 kilometers per second. The second, Comet Borisov, arrived at roughly 32 kilometers per second. Like them, 3I Atlas travels at extraordinary speed, showing that interstellar objects are almost always ejected violently and move fast enough to escape their home stars forever. This extreme speed also explains why spotting such travellers is so difficult. They pass through our skies very quickly, staying visible for only a short time, often just a few months. By the time astronomers confirm that they are interstellar, these objects are already fading into the distance. In the case of 3I Atlas, being discovered just before it reached its closest point to the Sun was a remarkable stroke of luck. That early detection allowed scientists to study it for a little longer than usual, though it still appeared and disappeared within less than a year. The breathtaking speed of 3I Atlas raises an exciting question. Could humans ever send a spacecraft to chase one of these cosmic visitors? With today's technology, the answer is no. An object moving at tens of kilometers per second would be far too fast for our current rockets to catch. Reaching it would demand incredible amounts of energy and perfect timing. Still, scientists hope that in the future, with faster spacecraft and earlier detection methods, humanity might one day be able to meet such a traveller from another star, and finally uncover the secrets it carries from its distant home. What makes the story even more amazing is how 3I Atlas was found. The telescope that noticed it in December of the year 2019 was not made to look for visitors from other star systems. It was part of the Atlas Survey, a project meant to watch the skies for asteroids and comets that might be dangerous to Earth. Run by the University of Hawaii and supported by NASA's Planetary Defense Coordination Office, Atlas uses wide-view Schmidt telescopes to scan the whole night sky over and over again, night after night. These telescopes are not the biggest in the world, but their power comes from how fast they work and how wide a view they can see. Right now, 4 Atlas telescopes are active, 2 in Hawaii, 1 on Mauna Loa and another on Haleakala, and 2 in the Southern Hemisphere, 1 in Chile and 1 in South Africa. Each telescope scans the sky several times every night, automatically marking anything that seems to move compared to the background stars. Most of these moving objects turn out to be ordinary asteroids or comets, but sometimes something unusual shows up, something faster, stranger, or moving along a path that has never been seen before. That is exactly what happened on the 12th day of December 2019. Atlas spotted a faint object moving faster than expected. At first, astronomers thought it was just another comet coming from the outer part of the solar system, and it was given the temporary name C2019Y4 Atlas. But later calculations showed that its orbit was hyperbolic, with an eccentricity greater than 1. That meant only one thing: it came from outside the solar system. After weeks of careful watching, the truth was clear. This was the third confirmed interstellar visitor, after Oumuamua and Borisov, and so it was officially named 3I Atlas. Unlike the first two, which were found later in their travels, 3I Atlas was spotted earlier before it came closest to the Sun. That gave astronomers several valuable extra weeks to study it as it became brighter. During that time, they studied its light, measured its brightness changes, and even tried to guess what it was made of. The Atlas system, even though it was not designed for this, had caught a real traveller from another star system before it disappeared forever into deep space. When the Atlas survey first noticed this strange visitor, astronomers around the world reacted quickly. Major observatories turned their telescopes toward it. The Pan-STARRS system in Hawaii, the twin telescopes of the Gemini Observatory, and even the famous Hubble Space Telescope. Together they started collecting all the information they could: the faint shimmer of its light, the soft shades of its colour, and the movement of its thin, ghostly tail. It was a rare moment of global teamwork, where many countries, telescopes, and tools worked together to study the object across all types of light, from the kind we can see with our eyes to the invisible warmth of the infrared. Without Atlas's sharp first detection, this worldwide effort might never have taken place. The discovery of 3I Atlas also showed how much skywatching technology has improved in just a few short years. Before the year 2017, no interstellar object had ever been found. It was not because they did not exist, they have always been out there, but because our tools were not sensitive enough to notice them. These visitors are tiny, dim, and move incredibly fast, slipping across the sky almost unseen. Only surveys that repeatedly scan large parts of the heavens can catch them. Atlas's success proved that we now live in a new age of discovery, an age when finding travellers from other star systems may become much more common. Looking to the future, scientists are already getting ready for even more discoveries. New sky surveys promise to change the search completely. The Legacy Survey of Space and Time, which will soon begin at the Vera Rubin Observatory, is expected to find many more of these interstellar wanderers. While Atlas, with its smaller tools, managed to spot 3I Atlas, the Rubin telescope will be far more powerful. With its huge mirror, about 8 4/10 meters wide, and its wide view of the southern sky, it will scan the heavens every few nights. This means it will be able to detect even fainter and more distant visitors long before they reach the Sun. Once telescopes had focused on this mysterious traveller, astronomers turned to two important clues: colour and reflectivity. Since no spacecraft can yet be sent to follow such a fast-moving visitor, the only way to study it is by analysing the sunlight it reflects. Every change in colour and every tiny flicker of brightness gives hints about its makeup, surface, and the distant place where it was born. When 3I Atlas was first studied, its light looked bluish-green, a colour often linked to comets that have fragile ices. That colour suggested that gases such as cyanogen and diatomic carbon were present, molecules that glow greenish-blue when sunlight hits them. These same molecules are common in icy objects that formed in the cold, outer regions of star systems, where ice can last for billions of years. From its colour alone, astronomers quickly realised that 3I Atlas was an icy, volatile-rich traveller, very different from rocky asteroids. Reflectivity, or albedo, gave more clues. Scientists found that 3I Atlas reflects only about 4 to 10% of the sunlight that hits it. This makes it nearly as dark as carbon-rich comets in our own solar system. Such low reflectivity suggests that its surface is covered with ancient carbon-based dust, organic material that has been darkened by endless years of cosmic radiation. Powerful particles from space strike its surface, slowly turning simple ices into complex organic compounds. Over millions of years, this builds up a dark reddish layer, like a natural shield, that gives the object its mysterious look. But 3I Atlas had another surprise. Its brightness changed over time. Beyond the normal flickering caused by jets of gas, its light seemed to rise and fall in a pattern. These small changes showed that the object is not perfectly round. Instead, it likely has an uneven shape, with some parts reflecting more light than others. Some areas might still have exposed ice that shines brightly, while other parts are covered by dark, weathered material shaped by long years in space. When compared with the first two interstellar visitors, 3i Atlas showed how unique it really is. The first, Oumuamua, found in the year 2017, had a strange reddish metallic glow, likely caused by strong space weathering. The second, Borisov, discovered in the year 2019, looked more like a normal comet, similar to those in our own Oort cloud. 3i Atlas sits between the two. Like Borisov, it seems icy and full of gases, but its weak activity shows that a thick layer of old material now protects its inner ices. The story told by its colour and brightness reveals a long and difficult journey. For millions of years, this object has survived the harshest parts of the galaxy: cosmic rays, dust grains, and the steady pressure of starlight. Slowly, its bright ices darkened, while deep inside, untouched ice remained frozen since the day it left its home system. The fact that it still gives off small jets of gas when warmed by the sun shows that much of its inside is still frozen and ancient. Spectroscopic studies, where sunlight is split into its different colours, showed that 3i Atlas contains common substances like water ice and carbon monoxide. But the balance between them is not quite the same as what we see in local comets. If it has more carbon monoxide, for instance, that means it probably formed farther from its star, in a much colder place, maybe like the outer Kuiper belt or even beyond. These differences could help scientists figure out whether its home star was like our Sun, or a smaller, cooler red dwarf. Its reflectivity also acts like a kind of space clock. A bright, icy surface means it was thrown into space only recently, while a dark, weathered one means it has been travelling for millions, or even billions, of years. The dull surface of 3i Atlas suggests it has been wandering for an extremely long time, long enough to build up its dark crust, but not long enough to lose all of its inner ice. By studying its reddish surface and the faint glow of its gases, astronomers gained something priceless: a direct look into the hidden history of other planetary systems. Each interstellar visitor is like a frozen sample from another world, carrying secrets from faraway parts of the galaxy. Together, they can help us learn whether our solar system is rare and special, or whether worlds like ours are common across the stars. Finding out how big 3i Atlas truly is has proven to be a real challenge. When scientists want to learn the size and shape of nearby asteroids or comets, they can simply send spacecraft to fly past them and take clear pictures. But this strange visitor is not from our solar system. It comes from far beyond and is much too distant for any spacecraft to reach. Because of that, astronomers have to depend on clever, indirect ways to estimate how large it really is. The main method they use is called photometry, which is basically the science of measuring how much sunlight an object reflects. By carefully observing how bright 3i Atlas appears in the night sky, and by making thoughtful guesses about how reflective its surface might be, a property known as albedo, scientists can estimate its size. If the comet's surface is shiny, covered with ice that reflects a lot of light, then it must be smaller. But if its surface is dark and dusty, like that of many old comets, then it must be larger because it reflects less sunlight. The first detailed measurements gave astronomers some exciting clues. They showed that even though 3i Atlas is small compared to planets, it is still noticeably larger than some of the other rare interstellar visitors we have ever seen. Early photometric studies suggest that its width lies somewhere between 60 meters and 120 meters. If its surface is coated with dark, carbon-rich dust, then it is likely toward the upper end of that range. But if it has bright, icy patches, it could be closer to the lower end. To understand what that means, it helps to compare it with the other two known interstellar travelers. The first one, Oumuamua, passed through our solar system in the year 2017. It was about 100 meters long, but its strange, stretched shape, almost like a cigar, made its size hard to measure exactly. The second visitor, Comet Borisov, was discovered in the year 2019 and was much larger, with a solid core over 1 kilometer wide. 3i Atlas fits neatly between them, closer in size to Oumuamua, yet more like a true comet in appearance. Interestingly, it is also similar in scale to many comets that belong to our own solar system. This suggests that interstellar comets may not be so different in size from the icy wanderers that orbit our Sun. Astronomers also noticed something curious. The brightness of 3i Atlas changes in a steady rhythm. This means it is not a perfect sphere. It may be stretched, uneven, or even shaped like a jagged chunk of rock and ice that once broke off from a larger world. As it spins, different parts of its surface catch sunlight and reflect it toward Earth, causing small flickers of light called a light curve. These flickers make it harder to calculate its true size because the changing angles of sunlight constantly alter its brightness. Another reason interstellar visitors like this are so rarely found is that they are usually quite small. Even when it was at its brightest, 3I Atlas appeared faint and could only be seen for a short time using medium or large telescopes. Considering how crowded the Milky Way's background is with stars, its discovery was truly remarkable. If it had been only half as big, scientists believe it would have remained completely invisible to us. Its small size also affects how strong it is. Tiny objects are usually more fragile and tend to break apart when they come too close to stars. In our own solar system, many comets that pass near the Sun are torn into pieces by its fierce heat and gravity. Yet 3I Atlas seems strong enough to survive mild heating and gravitational forces. Astronomers did notice a few weak jets of gas escaping from its surface, signs of ice turning into vapour, but that is normal for comets, and not a sign of destruction. The size of 3I Atlas offers important clues about what else might be drifting between the stars. If this object represents a common type, then the galaxy could be filled with countless similar icy fragments. Based on the discoveries of Oumuamua, Comet Borisov, and now 3I Atlas, scientists think there might be billions of such travellers silently crossing the spaces between stars. Most of them were likely thrown out of their home systems during the violent early years when planets were first forming. With new sky surveys coming soon, astronomers expect to find many more of these dim wanderers and finally understand how large or small these interstellar bodies usually are. Still, the smallness of 3I Atlas leaves behind deep questions. Could it once have been part of something far larger, perhaps a fragment of a shattered exoplanet or a dwarf planet that was torn apart by cosmic forces? Or was it born small and whole, ejected into space exactly as it is? Its strange variations in brightness and its possible stretched shape seem to support the first idea, that it might be a broken piece of a much bigger world. Computer simulations of planetary systems show that huge collisions and gravitational slingshots can fling such fragments across the galaxy, turning them into eternal wanderers. Whether 3I Atlas grows a glowing tail of dust like an ordinary comet, or behaves in a surprising new way, it has already given humanity something precious, a glimpse into the unseen world of interstellar debris. Though tiny compared to planets, this frozen visitor from another star helps connect the story of how planets are born to the larger tale of our continuing journey through the universe. When astronomers study a space traveller from another star system like 3I Atlas, one of the first questions they face is whether it behaves more like an asteroid or a comet. This question is not just about naming. It helps reveal what the object is made of and how much frozen material or easily melting ice is hidden inside it. The difference is important. Comets, when warmed by the sun, release gases from their icy surfaces in a process called turning straight from ice into gas. This often creates a glowing cloud of gas and dust, called a coma, and sometimes even a long sweeping tail that can stretch far across space. Asteroids, on the other hand, are usually much quieter. They are mostly dry and rocky, reflecting sunlight but showing no clear signs of gas or dust. 3I Atlas does not fit neatly into either group. Instead, it seems to sit somewhere in between, mixing the traits of both comets and asteroids. This in-between nature makes it especially interesting because it raises questions about how such travellers from other star systems change during their unbelievably long trips between the stars. When 3I Atlas was first spotted, astronomers noticed faint signs of activity. Careful measurements of its brightness, tracking how much sunlight it reflected, showed a thin, hazy glow around its centre. This meant that some of its frozen ices were melting as it came closer to the sun. The coma, however, was weak. It was stronger than the total stillness of Oumuamua, 1I Oumuamua, which had no visible coma at all, but much weaker than the bright display of Borisov, 2I Borisov, which created a classic comet tail tens of thousands of kilometres long. 3I Atlas therefore stands in the middle ground, active enough to show it has melting ice, but quiet enough to suggest that part of its surface is covered by a hardened or protective crust. The activity that astronomers saw was limited to a thin cloud of dust, rather than a grand tail stretching across the sky. This faint activity told part of its story. One idea is that 3I Atlas has been floating through interstellar space for millions of years. During that time, cosmic rays and tiny hits from space dust may have baked its surface, leaving behind a tough, dark crust. This shell could act like a seal, trapping deeper ice and stopping it from escaping, even when the sun's warmth reached it. Another idea is that 3I Atlas was never very rich in ice to begin with. It might have formed closer to its home star, in a warmer region than where most icy comets are born. If that is true, it may have been made mostly of rock, with only small traces of frozen gas left. Astronomers also compared how much dust it released. Borisov threw out hundreds of kilograms of dust every second, creating a stunning sight through telescopes. In contrast, 3I Atlas gave off only a few kilograms of dust per second at its most active. This weak release explains why it never formed the kind of sweeping tail that could be seen even with small backyard telescopes. Yet even this faint trickle of gas and dust was scientifically valuable. By studying the light from the thin coma, astronomers found signs of water vapor, carbon monoxide, and possibly carbon dioxide. These are exactly the kinds of ices that form in the cold outer parts of planetary systems. The strong presence of carbon monoxide was especially interesting because it suggests that 3I Atlas was born in an extremely cold place, maybe even farther from its star than the region of our own Kuiper belt. This supports the idea that such objects are thrown out from the icy edges of young planetary systems when giant planets fling them into the darkness of space. The lack of a large tail also offered clues about its inside. It seems likely that heat from the sun could only reach shallow depths inside its porous or cracked centre, causing gases to leak out slowly instead of bursting outward. Its surface, changed over ages by radiation and countless tiny hits, may have built up a hardened shell that protected deeper layers of ice from escaping easily. This raises a bigger question. Do all interstellar objects change in the same way, or do they each follow their own path? Borisov stayed rich in ice, showing strong activity. Oumuamua, on the other hand, showed no visible signs of gas at all. And 3I Atlas lies in between, showing a faint glow but no tail. Maybe some interstellar travelers develop protective crusts that silence their comet-like activity, while others stay mostly untouched, keeping their icy layers intact. These differences are not just small details, they help astronomers understand how the harsh emptiness of deep space reshapes icy bodies over millions of years. There is also a deeper idea behind all this. The faint glow of 3I Atlas links to the idea of panspermia, the thought that the seeds of life could move between stars on comets. If an object can still carry carbon-rich and icy material after such an unimaginably long trip, then it might act as a natural messenger for complex molecules. Even weak gas releases show that these compounds can survive the brutal cold and radiation of space, only to be set free again when such a traveller passes near a star. By comparing Oumuamua, Borisov, and now 3I Atlas, astronomers are beginning to see the amazing variety of these visitors. Each tells a different story, and together they paint a picture of how mysterious and diverse the building blocks of distant worlds can be. When astronomers discovered the first travellers from other star systems, they saw that each one seemed to have its own unique character. The very first, Oumuamua, was a mystery wrapped in silence. It showed none of the usual outbursts of a comet, yet its strange movement in space hinted at hidden forces. Some scientists thought it might be covered in shiny metallic hydrogen, while others believed it could have an ancient organic crust. In complete contrast, the second visitor, Borisov, behaved exactly like the comets we know in our solar system. It followed the textbook pattern, releasing gas and dust, forming a coma, and developing a tail under the sun's warmth. Now, standing between these two extremes is the third interstellar traveller, 3I Atlas. It is icy like a comet, yet its surface seems partly sealed by an old crust that hides some of its inner activity. It is active, releasing material into space, but not in a violent or explosive way. This middle ground behaviour supports an exciting idea. Interstellar objects are not all alike. Instead, they likely represent a wide range of space travellers, each shaped by its birthplace, its journey across billions of years, and the empty cold of space. One of the most important things to learn about 3I Atlas is how it spins, whether it turns smoothly, tumbles unevenly, or something in between. This may sound like a small detail, but it is actually very important. The way an object spins decides how sunlight warms its surface, and in turn, where and how gas and dust escape into space. A tumbling spin might reveal hidden icy spots from time to time, causing sudden bursts of activity. On the other hand, a steady and even spin would spread out the heating more evenly, creating calmer releases. By studying how 3I Atlas spins, astronomers can start to uncover its inner structure, its surface behaviour, and even clues about its long history. To measure its spin, scientists use light curves, the faint but repeating changes in brightness as the object turns in space. Much like a lumpy potato reflects different amounts of sunlight as it turns, 3I Atlas flickered with small variations that showed its spin. These changes were not dramatic, but they were clear enough to confirm that it is indeed rotating, and not just still. The early data suggests that its spin takes about 9 to 12 hours to complete one full turn. This speed is not unusual. Many comets in our solar system also spin within a range of a few hours to a full day. Its moderate spin is important. It shows that 3I Atlas is strong enough to survive its long trip through space without breaking apart, but also not spinning so fast that forces could tear it to pieces. Yet the story does not stop there. The light curve showed something more interesting. Instead of following a smooth wave-like pattern, its brightness had uneven peaks and dips. This suggests that the object is probably not a neat sphere but rather stretched out or irregular in shape. It might also mean that 3I Atlas is not spinning around a single stable axis, but instead is caught in a tumbling state, what astronomers call non-principal axis rotation. Tumbling is not rare. Small bodies in space often end up tumbling after close gravitational encounters or tiny impacts. For an interstellar traveller, this makes perfect sense. As 3I Atlas wandered through the galaxy for millions of years, it would have felt gentle pulls from passing stars and may have been struck by tiny bits of space dust. Over time, these small nudges can disturb a smooth spin, sending the object into a wobbling, uneven motion. Its patchy coma and uneven dust release might also be explained by this tumbling, since sunlight would hit different areas at unpredictable times, causing uneven bursts. If it is indeed tumbling, that also tells us something about its strength. A fragile object would likely break apart under such stress. The fact that 3I Atlas can handle this suggests it has enough inner strength, possibly held together by a tough mix of ice and compacted dust. The way 3I Atlas spins tells astronomers more than just how it moves now. It carries clues about its long history and its encounters with other stars. Every time a small object passes near a star, the heat can make trapped gases escape, creating small, repeated pushes that slowly change its spin. Over many such close passes, an object can start spinning faster and faster, sometimes so quickly that it could even break apart. The fact that 3I Atlas has a moderate spin suggests two main possibilities. Either it has only passed near a few stars during its long journey through space, or its outer shell has acted like armour, keeping its gas releases gentle and steady. Another idea is that its unusual spin goes all the way back to the violent moment it was thrown out of its original star system. In the early days when planets were forming, huge planets often acted like cosmic slingshots, flinging smaller objects out into space. 3I Atlas might have been launched by one such giant world. That close encounter could have set its spin in motion, a kind of cosmic fossil preserving the moment its incredible journey began. When astronomers compare 3I Atlas with other interstellar travellers, it seems to sit somewhere in the middle. Oumuamua tumbled wildly and may have been stretched out like a long cigar. Borisov, on the other hand, spun more evenly, like the comets we know. 3I Atlas shows traits of both. Its spin is moderate, but maybe a little unstable, showing that interstellar objects come in many shapes, sizes and histories, each carrying a story written in the way it turns. Spin is only one part of the puzzle. Another main tool scientists use is spectroscopy, the study of light reflected or given off by an object. By looking at sunlight bouncing off its surface or passing through the gas around it, researchers can identify certain atoms and molecules. Each element and compound leaves a unique fingerprint in the light. For a traveller from another star system, these fingerprints are like messages from another world, giving a direct look into the chemistry of a distant place. When astronomers studied the spectrum of 3I Atlas, they found something surprising. Even though it came from another star system, it looked very familiar. Its light showed many of the same ingredients found in comets that orbit our Sun. This discovery hints at something amazing, that the way comets form may follow similar patterns all across the galaxy, happening in star systems far beyond our own. The clearest sign astronomers found came from water ice, seen as gentle dips in the near-infrared part of the light spectrum. Water is one of the most common ingredients in the entire universe. It exists almost everywhere, on planets, moons, comets, and even floating freely through the emptiness of space. Its presence told scientists that 3I Atlas must have been born in a cold and distant part of its original solar system, far away from the warmth of its home star. But the story did not end with water. The object also gave off gases such as carbon monoxide and carbon dioxide, substances often found in comets from our own solar system. However, the exact amounts of these gases can change depending on where and how a comet was formed. In the case of 3I Atlas, astronomers noticed that it seemed to have a bit more carbon monoxide compared to water than most comets from our Kuiper belt. This suggests that it may have formed even farther from its parent star than the comets we know, perhaps because that star was cooler or dimmer than our Sun. If so, the icy materials that built 3I Atlas would have gathered at much greater distances in the coldest and darkest parts of its system. When scientists studied the light more closely through spectroscopy, they also found faint signs of more complicated molecules, possible organic compounds and hydrocarbons. These appeared as delicate absorption patterns in ultraviolet and near-infrared light. Such molecules were likely formed when powerful cosmic rays slowly changed the chemical makeup of its icy surface during its long and lonely trip through interstellar space. This same process happens to long-period comets and faraway icy worlds in our own solar system. Over billions of years, their surfaces darken and turn reddish as radiation reshapes their chemistry. The discovery of organic molecules was especially thrilling because it adds to the growing belief that the basic chemistry linked to life might be common throughout the galaxy. As 3I Atlas released its gas and dust, it was not only spreading water and carbon compounds, but also sending out tiny organic particles into the void. Some of these particles could one day wander into nearby star systems, perhaps landing on young planets. Over countless billions of years, travelers like this may serve as galactic messengers, carrying the building blocks of life from one star system to another across the Milky Way. The data also gave scientists clues about how ancient and well-preserved its material might be. Some interstellar visitors, like Comet Borisov, appear almost identical in makeup to the comets found in our solar system, as though they were frozen snapshots from long ago. But 3I Atlas told a slightly different tale. Its outer layer looked weathered and scarred by radiation, while the ice beneath seemed untouched and fresh. This pattern, a worn outer shell protecting younger, cleaner ice inside, is exactly what experts expect to see in a true interstellar object that has travelled for ages through space. More evidence came from the discovery of silicate dust in its glowing gas cloud, which showed up as bright peaks in the infrared light. Silicates are rocky materials that form closer to a star, where temperatures are higher. This finding proved that 3I Atlas was not just a ball of ice, it was a blend of rock and ice. It likely took shape in a middle region of its home system, a place between the hot inner planets and the frozen outer belt. This fits with the idea that many interstellar comets are thrown out of their birth systems when they are still young, during chaotic times when planets and asteroids are being jostled by gravity and material from different zones mixes together. Perhaps the most surprising discovery was also the simplest. Aside from small differences in gas ratios and the effects of long-term radiation, 3I Atlas contained no strange or unknown substances. In many ways, it was remarkably ordinary. Yet this very normality carries a deep meaning. It shows that the same kind of chemistry shaping comets in our own solar system is taking place all across the galaxy. The ingredients for planets, oceans, and possibly even life itself are not rare treasures hidden in one corner of the cosmos. They are scattered everywhere, waiting to be gathered and brought to life on countless other worlds throughout the Milky Way. When astronomers speak of visitors from outside our solar system, three names shine brightly in their minds: 1I Oumuamua, 2I Borisov, and the more recent 3I Atlas. These mysterious travelers are like messages written in starlight, each carrying clues about the distant worlds they once called home. Comparing these three wanderers is not just a scientific exercise, It is like studying 3 pages torn from the vast diary of the galaxy, each page telling a different story about how planets and comets form, evolve, and survive the endless ages of space. The discovery of 3I Atlas was a moment of wonder. It marked only the 3rd time in all of human history that astronomers had ever been able to study an interstellar object up close. Each of these visitors is unique, its life story shaped by the star system where it was born, the violent event that hurled it into the cosmic void, and the countless millions of years it spent wandering alone through the frozen darkness between the stars. By comparing 3I Atlas with its predecessors, scientists hope to understand what kinds of materials other star systems produce and how these materials transform as they travel through the galaxy. The differences among these objects are most obvious in how active they are and what they look like to observers here on Earth. 2I Borisov was unmistakably a comet, a beautiful classic one. It grew a glowing green coma and a long shimmering tail, just like the comets we often see from our own solar system. When scientists studied its composition, they found something very familiar: the same frozen ices and dust that make up comets born near our Sun. This showed that the basic recipe for making comets seems to be the same no matter where in the galaxy they are formed. Oumuamua, on the other hand, could not have been more different. It had no glowing coma, no tail, no glittering jets of gas or dust. Instead, it looked more like a bare, rocky asteroid, a dry traveller hardened by time, with any remaining ice buried deep inside a tough, weathered crust. It moved silently through space, giving away almost no clues about what it was made of. 3I Atlas seemed to rest between these two extremes. It did show a faint touch of comet-like activity, proving that a little of its ancient ice still survived. But compared to Borisov's dazzling outburst, Atlas's faint halo of gas and dust was barely visible. Much of its surface had been sealed by a hard outer layer, formed as it drifted for untold ages through harsh interstellar radiation. Yet it was not completely lifeless like Oumuamua. Sensitive instruments caught traces of water vapour and carbon monoxide escaping from within, evidence that deep inside some untouched frozen material still remained. The chemistry of these cosmic wanderers deepens the mystery. Borisov contained familiar substances: water ice, carbon monoxide and carbon dioxide, in proportions much like those in comets of our own solar system. Oumuamua, though silent and inactive, had a reddish surface that hinted at the presence of organic compounds, molecules that had been scorched and weathered by cosmic rays for millions of years. 3I Atlas, once again, stood between the two. The light reflected from its surface revealed water ice, carbon monoxide, and perhaps even complex hydrocarbons. This mixture suggests it formed in the icy outskirts of a distant planetary system, but had been changed by its long journey through interstellar space. Even their shapes and motions tell intriguing tales. Oumuamua was the strangest of all. Its shape was unusual, possibly long and cigar-like, or thin and flat like a pancake, and it tumbled chaotically through space. Its odd behaviour inspired bold theories. Some said it could be a fragment of a shattered world, a block of frozen hydrogen, or even an artificial probe sent by another civilization. Borisov, in contrast, behaved like an ordinary comet. It had a roughly round nucleus and rotated steadily, showing nothing unexpected. 3I Atlas once more took the middle ground. Its brightness patterns hinted that it might be slightly elongated and slowly tumbling, though far less wildly than Oumuamua. This suggests it experienced a powerful ejection from its home system, but stayed mostly intact instead of breaking apart. Their sizes also show how different they are. Borisov was the largest, with a nucleus more than 1 kilometre wide, large enough to be seen with small backyard telescopes. Oumuamua was tiny by comparison, only about 100 metres long, and would have gone completely unnoticed without today's advanced sky surveys. 3I Atlas was smaller still, estimated to be between 60 and 120 metres across. Its small size explains why it was so hard to spot, and why it remained visible for such a short time before fading back into the darkness. Why do these visitors behave so differently? Their levels of activity reveal not only what they are made of, but also how old they are, and how long they have been travelling. Borisov's fresh, ice-rich nature shows it was ejected from its home system fairly recently, before cosmic radiation could strip it bare. Oumuamua, with its hardened, inactive surface, seems to have journeyed through interstellar space for countless eons, long enough to lose nearly all traces of its original ices. 3I Atlas, showing faint but definite signs of activity, seems to sit between these extremes, ancient and weathered, but not completely sealed. Their birthplaces hold clues too. Borisov likely formed in a system very much like ours, in the frozen outer regions beyond giant planets where comets are naturally born. Oumuamua's origins are still a mystery, but its dry, radiation-processed surface suggests it may have formed closer to its parent star in a warmer zone, or perhaps broken off from a larger rocky body. 3. I Atlas, with its high carbon monoxide content, hints at a colder birthplace, possibly in the farthest outskirts of a dim star system, where ices form at immense distances from the central sun. Some scientists even suggest that it could be a fragment of a planet, a small piece of a larger world that was torn apart long ago. Each of these interstellar travelers is a messenger from beyond, carrying silent stories written in ice, dust, and stone. Together, Oumuamua, Borisov, and Atlas remind us that our galaxy is full of wanderers, and that every now and then one of them crosses our path to whisper a new secret about the distant stars. One of the most exciting ideas about 3I Atlas is that it might not be an ordinary comet at all. Some scientists think it could be something much more dramatic, a piece broken off from a larger world. A chunk of ice and rock, once part of a planet or moon, could have been torn away in a violent crash and thrown into the endless space between stars. Although this idea is bold, clues in its size, shape and makeup suggest it does not match the usual pattern of a normal long-period comet. If this daring idea is true, 3I Atlas would give us a rare chance to study raw planetary material from inside another solar system. It could be the fossil of an ancient moon, or a piece of a faraway planet's outer layer. The thought that space between the stars might be filled with broken pieces of worlds is not impossible. The birth of planets is not peaceful. It is messy and violent. In the early life of a star system, young planets and moons crash into each other often as they settle into stable paths. Huge impacts can break apart whole worlds, sending debris flying like cosmic shrapnel. Giant planets make things even more chaotic. Their strong gravity can act like a slingshot, hurling rocks and ice into interstellar space. Computer models show that for every planet that stays whole, countless smaller bodies are thrown into space. Over billions of years, this could fill the galaxy with trillions of wandering fragments of shattered worlds. Several traits of 3I Atlas support the idea that it might be one of these fragments. Its brightness changes in a way that hints it has an uneven, stretched shape. Unlike most comets, which are roughly round, it looks rough and broken, more like shattered debris than a smooth core. Its light flickers as it spins, suggesting sharp edges and marks from a violent past. Its makeup is strange too. Studies of its light show both icy material and rocky dust, signs that it may not be a pure comet. Instead, it could be a piece of a layered world, one where heavier rocks sank to the centre and lighter ices rose to the top. If such a world was destroyed, a fragment like 3I Atlas could contain both rock and ice, explaining why it shows weaker activity than Borisov. Adding to the mystery, its surface is unusually dark, covered with carbon-rich organic material. Over millions of years, cosmic radiation weathers interstellar objects, but a planetary fragment would have started with a more complex mix of rock, ice, and minerals than a simple comet. Radiation slowly darkens its outer layer, leaving the blackened surface we see today. When we compare 3I Atlas to Oumuamua, the first interstellar visitor ever seen, the similarities are even more fascinating. Oumuamua was also long, inactive, and mysterious, so strange that some scientists thought it might be a piece of a planetesimal, a small building block of a planet, torn apart by the gravity of its parent star. 3I Atlas, while showing a bit more activity like a comet, still seems to sit between Oumuamua's quiet, broken form and Borisov's bright, icy display. It's as if these objects form a range, from silent fragments to active comets, each telling its own story from across the stars. If 3I Atlas really is a piece of a planet, it must have been thrown out under much more violent conditions than the gentle pushes that usually send comets drifting from their home systems. Most comets are slowly nudged outward by gradual gravitational effects, taking ages to leave their stars. A planetary fragment, though, would need a disaster, perhaps a huge planet moving inward and scattering smaller rocky worlds, or a passing star disturbing the entire system. Far from rare, such violent events are now believed to be common in young star systems, as studies of exoplanets have shown. The early galaxy was a rough nursery, with worlds colliding, breaking apart, and being flung into space. The meaning of this idea is huge. If 3i Atlas is a piece of a planet, interstellar objects are not just space oddities, they are tiny messengers carrying pieces of alien worlds. By studying what they are made of, astronomers can uncover the hidden layers of faraway planets, layers we could never see by just observing their surfaces. If 3i Atlas contains minerals, ices, or compounds unlike anything in our solar system, it would show that planets around other stars can form in completely different ways. Even more exciting is the thought that such fragments could help spread life. Could pieces of planets act as tiny ships, carrying the seeds of life from one star system to another? While the odds are small, large rocky fragments could protect delicate organic molecules from harsh radiation for millions of years. If even one fragment survived long enough to land on a young habitable world, it could deliver the ingredients needed for life, a concept known as panspermia. Proving that 3i Atlas is a planetary fragment, however, is not easy. Almost everything we know comes from indirect observations, since we do not yet have a sample. For now, it remains a mystery, one that future discoveries may help solve. As astronomers find more interstellar objects, patterns may appear, some acting like regular comets, others showing signs of broken planets. Yet if such fragments are common, why have we only seen 3 so far? The first was Oumuamua, the second Borisov, and the third 3i Atlas. Considering that countless planets and stars in the galaxy are likely sending out comets, asteroids, and planetary pieces, it seems amazing that we've spotted any at all. The reason lies not in rarity but in difficulty. Interstellar objects are probably everywhere, but they are extremely hard to detect. Several things make them so tricky to find. First is size and brightness. These visitors are usually very small, only a few dozen to a few hundred meters across, about the same size as 3i Atlas. Compared with planets or even large asteroids, they are tiny. Their small size means they reflect very little sunlight, and their surfaces are often darkened by cosmic radiation over billions of years. Many, like 3i Atlas, reflect only 4 to 10% of the light that hits them, making them almost as dark as charcoal. Unless they pass very close to Earth or form a bright glowing tail like a comet, they remain nearly invisible among the countless stars. Second is speed. Interstellar objects move much faster than comets and asteroids that formed in our own solar system. They race through space at tens of kilometers per second, crossing the inner solar system in just a few months. By the time they're close enough to see, they're already speeding away, giving astronomers only a short time to study them. Oumuamua, for example, was found after it had already passed the Sun, leaving scientists only a few weeks to observe it before it disappeared forever. Third is sky coverage. For a long time, we simply weren't looking carefully enough. Older sky surveys focused on bright stars, planets, and galaxies, not on small, faint objects moving quickly. Even surveys meant to find near-Earth asteroids, like the Atlas project, only scan certain parts of the sky each night, leaving large gaps unobserved. Finding a faint, fast-moving interstellar object among billions of stars is like spotting a single drifting leaf in a stormy sea. Another problem is that these travelers brighten only when they come close to the Sun. Far out in cold space, they are too dim to see. Some glow only when sunlight warms their surfaces, but even then, many stay faint. Oumuamua, for example, never formed a comet-like tail and stayed dim even at its closest point. Many visitors may have already passed through our solar system without being noticed. Still, computer models show that interstellar objects are extremely common. Astronomers think that for every star in the Milky Way, there may be trillions of icy and rocky fragments drifting through space. Most were thrown out billions of years ago during the violent early days of planet formation. Our own solar system likely sent out countless comets and asteroids as Jupiter and Saturn shifted their orbits. Other systems did the same, filling the galaxy with wandering debris. The universe may be full of these silent travelers, we just can't see most of them. Even so, progress has been fast. In just over 6 years, humans have gone from spotting none of these objects to finding 3. This big step forward is thanks to powerful sky surveys like Pan-STARRS and Atlas, which watch the skies every night for anything that moves unexpectedly. the future looks even brighter. The upcoming Legacy Survey of Space and Time, using the Vera Rubin Observatory's giant mirror and fast wide-field camera, will scan the heavens and may discover dozens or even hundreds of interstellar objects every decade. Yet most will still go unseen. Many will pass too far from Earth to detect, and many will be only tens of meters wide, smaller than 3I Atlas. These tiny wanderers will slip quietly through the solar system, unknown and unrecorded. Still, the few we do find teach us a lot. One of the first clues about an object's nature comes from its light curve, the way its brightness changes over time. These changes show whether the object is smooth or rough, round or stretched. For 3I Atlas, its brightness rises and falls steadily every 9 to 12 hours, matching its spin. The changes are mild, showing it's not as stretched as Oumuamua, whose brightness changed by a factor of 10 because of its extreme cigar or pancake-like shape. Yet the uneven peaks suggest a bumpy, irregular surface, possibly marked by ridges, craters or cracks, a cosmic fragment still showing the scars of its long journey between the stars. Unusual shapes are exactly what astronomers expect from travellers between the stars. Unlike planets and moons, which are pulled into almost perfect balls by their gravity, small rocky and icy objects often stay oddly shaped and uneven. Pieces from crashes, tidal breakups near stars, or gravitational slingshots can be thrown into space with rough, jagged edges. 3I Atlas's uneven shape may hold the memory of such violent events, maybe even linked to the exact moment it was thrown out of its home system. Its uneven brightness also gives clues about what its surface is made of. One side may be darkened by old, radiation-changed material, while another side might shine with fresh ice. Studies of its light already point to this patchy mix, showing why its brightness changes in a bumpy, uneven way instead of smoothly. Interestingly, the brightness changes are not extreme, hinting that over millions of years, 3I Atlas may have lost some of its sharpest edges. Tiny hits from spacedust and the slow turning of ice into gas would act like a kind of space sandpaper, slowly smoothing its shape. Yet it is still far from round or geologically alive, a small, quiet traveller from another star, marked but lasting, carrying the silent story of its amazing trip across the galaxy. When astronomers look at the shape of 3I Atlas and compare it to the two interstellar visitors that came before, the differences stand out clearly. Oumuamua, the very first known traveller from another star, had an extremely strange, stretched-out shape, so odd that some scientists thought it might be just a piece of a bigger object that had broken apart, or even a thin sheet of unusual material, maybe like a folded block of frozen hydrogen. 2, Borisov, the second interstellar visitor, was almost the opposite. It acted just like a normal comet from our own solar system. Its main body, or core, was quite round, and its brightness barely changed at all, giving it a very normal, familiar look. 3I Atlas sits somewhere in between. It does not look like a neat whole comet core. Instead, it seems more like a chunk of ice broken off from a larger frozen world. It is uneven, yes, but not beyond understanding. The shape of these objects also affects how they react when sunlight hits them. An uneven body warms unevenly. Some parts, covered with a hard crust, may stay quiet, while others, where fresh ice is open to space, can suddenly burst out with jets of gas. These jets can shoot out from only a few active spots, pushing the object like tiny rocket engines firing. Over time, this slow battle of heat, ice and gas can even change how the object spins, making it wobble or gently speed up or slow down. The small, flickering changes in 3I Atlas's brightness could be caused by exactly this quiet struggle between sunlight and ice. But another question comes up. Does its uneven shape make it weak? Compared with solid, round bodies, jagged pieces often do not hold together as well. If 3I Atlas were ever to pass too close to a star, or feel the crushing pull of strong tidal forces, it might break apart more easily than a solid, compact object. Yet the fact that it has survived its trip through our solar system shows that, even with its uneven shape, it is still strong, held together tightly enough to survive moderate heat and gravitational stress. Even so, many details remain unclear. 3I Atlas is faint, and astronomers struggle to see its outline clearly. They keep improving their models of its shape by combining careful brightness measurements with calculations of how it turns. Still, with the limits of today's tools, much about its real form is still hidden. In the years to come, though, powerful new observatories, like the Vera C. Rubin Observatory, may finally show the shapes of interstellar objects like this in much greater detail. With those sharper views, humanity might one day learn not only what these wandering pieces look like, but also the dramatic stories of their violent beginnings and long, lonely travels through the galaxy. When astronomers first realized that 3I Atlas was not just another normal comet or asteroid from our solar system, but a real visitor from faraway stars, moving at amazing speeds, a natural question quickly came to mind. Could this strange and mysterious traveller ever be a danger to Earth? The answer, thankfully, is a clear no. 3I Atlas is moving through space so fast that it never had any chance of hitting our planet. In fact, just like the other known interstellar visitors, its path through the solar system is such that it never even comes close to Earth. This safety is because 3I Atlas follows what scientists call a hyperbolic path. Unlike the oval orbits of planets and most comets, which are closed loops shaped by the sun's pull, a hyperbolic path is more like a one-way road through the solar system. The object enters, passes by, and then keeps going out, never to return. It is a one-time visitor, a guest from another star passing through only once before disappearing forever into the vast emptiness between the stars. Even when 3I Atlas came closest to the Sun, at the point astronomers call perihelion, it never came near the inner planets where Earth, Venus and Mars move. Its closest approach to the Sun was about 0.3 astronomical units, around 45 million kilometers. To make that easier to picture, this is roughly the same distance as Mercury's orbit, the innermost planet of our solar system. Earth, in comparison, sits at 1 astronomical unit from the Sun, more than 3 times farther away. In other words, 3I Atlas stayed far outside Earth's neighbourhood, quietly moving through space without any danger to our world. Even if, by some cosmic chance, its path had been slightly different, the object's amazing speed would have kept us safe. At its fastest, 3I Atlas was travelling around 60 kilometres every second, almost 10 times faster than a normal comet from our solar system. At such a high speed, it would have shot past any planet before gravity could pull it in or even slow it down much. This incredible speed alone made a crash practically impossible. Astronomers carefully worked out the closest possible distance it could come to Earth or any other planet to confirm that there was no risk. These calculations are not only important for safety, they also help scientists understand how interstellar objects move when they pass through our solar system, giving clues about their long journeys. Interestingly, while 3I Atlas never came near Earth, it did pass a bit closer to the giant planets Jupiter and Saturn. These huge worlds, with their strong gravity, gave the traveller small pulls as it went by. Though these tugs were gentle and did not change its path much, they slightly bent its course, like a light breeze changing the path of a drifting leaf. By studying these small gravitational effects, astronomers can fine-tune their models and improve predictions for the next interstellar visitors. Even though 3I Atlas will soon vanish again into the dark of interstellar space, leaving our solar system for good, its short visit has already taught scientists many important lessons. It is a bright reminder that the galaxy is full of high-speed travellers, many of which could pass much closer to Earth someday. The next one might not be so far away. That is why astronomers stress the need to find these objects as early as possible, long before they reach their closest point. Today, new observatories like the Vera C. Rubin Observatory, along with advanced sky surveys, are being set up to scan the skies more carefully than ever before. With these powerful tools, we may find many more of these rare travellers from other star systems, giving humanity the time to study them and uncover their secrets. For now, 3I Atlas stands as only the 3rd confirmed interstellar object ever found. Yet as technology improves and our cosmic vision becomes clearer, discoveries like this will likely become more common. One of the most fascinating, and at the same time most frustrating, things about studying 3I Atlas is how incredibly short its visit to our skies really was. Ordinary comets and asteroids that belong to our solar system can stay visible for years, sometimes even decades, as they circle the Sun again and again. But interstellar travellers like 3I Atlas are nothing like them. They appear suddenly from the darkness between the stars, rush through the inner solar system at breathtaking speed, and then disappear forever into the vast star-filled night. Their stretched one-way paths mean that once they have passed, we will never see them again. For astronomers, this fleeting visit created a race against time. Every day, every hour, and even every single minute mattered. A moment of hesitation could mean losing the only chance to study this mysterious traveller before it vanished forever. When 3I Atlas was first discovered by the Atlas Survey in December of the year 2019, it was already moving at an astonishing speed through deep space. The scientists who spotted it quickly realized that this was no ordinary comet. While comets that belong to our solar system often return after thousands or even millions of years, 3I Atlas was on a one-way journey. It was a true wanderer from another star system, visiting us just once before continuing its endless voyage through the galaxy. Every day that passed shortened the precious opportunity to study it. At the time of its discovery, 3I Atlas was still hundreds of millions of kilometers from the Sun. But as it drew closer, the Sun's warmth began to melt its icy surface, releasing gas and dust that formed a glowing cloud around it, known as a coma. This made the comet appear brighter and easier to observe, but only for a short while. Its brightness reached its highest point just before its closest approach to the Sun, known as perihelion, in May of the year 2020. After that moment, as it moved away again, its glow quickly faded. The Sun's heat stripped away its delicate halo of dust and gas, leaving it fainter and harder to see. Because the window to observe 3I Atlas was so brief, every measurement and photograph became priceless. In total, it was visible from Earth for only a few short months. Astronomers across the world worked together, using telescopes on different continents to collect as much data as possible before it disappeared. Only the most powerful observatories, equipped with highly sensitive instruments, could keep track of it as it grew dimmer and drifted farther away. In the years to come, new observatories like the Vera C. Rubin Observatory, designed to scan the sky with incredible speed and precision, will allow scientists to detect such fleeting visitors much earlier. But when 3I Atlas appeared, its brief moment in the cosmic spotlight was already fading. The story of 3I Atlas reminds us just how rare and short-lived encounters with interstellar objects can be. They move so quickly across such immense distances that astronomers often have only weeks or months to study them before they vanish forever into the darkness. For 3I Atlas, researchers had just a small window to measure its orbit, study its chemical makeup and watch its activity. After perihelion, its brightness dropped rapidly, and soon it disappeared completely into the endless void of space. This urgency is not just about scientific curiosity, it also has importance for planetary safety. Although interstellar objects like 3I Atlas travel so fast that the chances of them colliding with Earth are extremely small, finding and studying them remains crucial. By understanding how often these travelers appear, how they behave and what they are made of, scientists can better predict any possible future risks. The development of faster sky surveys and better early warning systems will be vital for spotting such elusive visitors before they slip away again. The brief glimpse we had of 3I Atlas also shows how precious every interstellar discovery truly is. To observe an object that was born around another star is a rare honour, something that might happen only once in a generation. By studying its dust, gas and structure, astronomers not only learn about this single comet, but also about the wider galaxy. What kinds of stars give birth to these drifting fragments? How do they change as they wander through interstellar space for millions or even billions of years? What secrets of alien chemistry lie hidden within their dust? The behaviour of dust around 3I Atlas offered some important surprises. In our own solar system, comets are famous for their long, shining tails that sweep across the sky. These tails form when sunlight heats the comet's icy surface, turning frozen gases directly into vapour in a process called sublimation. As the gas escapes, it carries dust particles along, forming a bright, glittering trail that can stretch for millions of kilometres through space. But 3I Atlas did not behave like the lively comets we know so well. Instead of a bright, flowing tail, its dust activity was weak and uneven, almost ghost-like. This puzzled astronomers and raised an exciting question. Could interstellar comets be very different from the ones born in our own solar system? When another interstellar visitor, Comet Borisov, passed through our system in the same year, 2019, it displayed a clear, shining dust tail that could be seen even with medium-sized telescopes. 3I Atlas, by contrast, showed only a faint, dim halo of dust, so weak that even the largest telescopes in the world struggle to detect it. This striking difference suggested something remarkable, that interstellar comets might not all look or behave alike. Instead, they may be far more diverse and surprising than anyone had ever imagined. Comets in the solar system usually contain large amounts of easily evaporating ices such as water, carbon monoxide, and methane. These substances turn into gas quickly when heated, which is why many comets in our solar system grow huge, glowing comas and long tails. 3I Atlas, however, seemed different. Its weak, ghostly cloud of dust suggests that it may contain less of these easily melting materials. Instead, it could be made of tougher substances, rocky pieces or carbon-rich organic material, that do not turn into gas as easily and need much more heat to release any gas. Even so, the faint glow shows that 3I Atlas was still releasing gas, though at a much lower level than most comets in our solar system. This suggests that its surface has probably been hardened over very long ages by cosmic radiation during its long trip through the cold emptiness of the Milky Way. Radiation over millions or even billions of years can bake the outer ice layers into a dark crust, working like a shield and keeping the inner ice from escaping. As 3I Atlas got closer to the Sun, only its outer layers warmed enough to release small amounts of gas and dust, forming a thin haze, but not the big, bright tail that Borisov showed so clearly. The slow flow of dust also gives clues about where the comet may have come from. The presence of silicate grains, tiny rocky minerals in its faint coma, suggests that 3I Atlas may have come from a planetary system where rock and ice were mixed together. Perhaps it was once part of a bigger object, like a moon or a planetesimal, that was broken apart and thrown into interstellar space. If that is true, then 3I Atlas is not just a visitor from another star system, but a piece of a much larger and more complex world. The way its dust behaves reminds scientists that not all comets are the same. Some, like those from the Oort cloud in our solar system, hold lots of ice that bursts into gas dramatically when heated. Others, like 3I Atlas, may have drifted through interstellar space for so long that their surfaces have become hardened, their ices buried, and their activity dimmed. This leads to an exciting idea. Interstellar comets might carry hidden stories about the worlds they came from. Their chemical makeup, surface texture, and even how bright or dim their dust tails are could reveal the long cosmic histories they've lived through. In the case of 3I Atlas, its weak dust halo tells of a journey across the galaxy lasting countless ages, of endless exposure to radiation, and maybe even of an origin as part of a broken planetary body. Astronomers are still trying to understand the true nature of 3I Atlas. Could it really be just another ordinary comet, or is it something far more unusual, a fragment torn from a much larger world? One of the most exciting ideas is that 3I Atlas might actually be a piece of a planetesimal, a small original building block of planets. Planetesimals are the first seeds from which planets grow. In the early stages of a young star system, these small rocky and icy bodies form naturally as gas and dust come together. Sometimes gravity makes them crash gently and merge into bigger objects that later become moons or full planets. Other times, violent crashes or the strong pull of giant planets break them apart. If 3I Atlas is truly such a fragment, then what we are seeing is not just a normal comet, but a rare leftover piece of another planetary system, thrown into the dark emptiness of interstellar space millions or even billions of years ago, long before it entered our own solar system. Planetesimals are very important for understanding how planets and moons are made. Even today, around our Sun, many of them still float quietly in places like the asteroid belt between Mars and Jupiter, or the faraway Kuiper belt beyond Neptune. Yet some do not stay put. When giant planets disturb their paths or huge crashes occur, these bodies can be thrown out completely, sent drifting through the galaxy. They may travel for unimaginable lengths of time, millions or even billions of years, before crossing paths with another star system. This is the kind of long journey that might have brought 3I Atlas to us. Several hints suggest that this interstellar traveller could really be a piece of a larger object. First, its chemical mix is unusual. While most comets are mostly made of frozen gases and dust, 3I Atlas holds a mix of ice and rocky minerals. Among them are silicate minerals, materials that normally form closer to a star in the warmer inner parts of a planetary system. This strongly suggests that it once belonged to a larger, more complex world, maybe a small moon or a planetesimal that had heat inside, which separated rock from ice. Such bodies are far more advanced than ordinary comets, which usually stay as untouched balls of ancient ice. Second, its shape and changing brightness tell a vivid story. 3i Atlas is irregular, stretched, and uneven rather than round and smooth. This fits what astronomers expect from an object that has been broken by a crash or shaken by gravity. Watching its light curve, how its brightness changes as it spins, shows that it is no simple ball, but a rough survivor of an ancient cosmic collision. Unlike many active comets, 3i Atlas has only a faint coma, the glowing cloud of gas and dust that normally surrounds a comet as it gets close to a star. Its weak activity shows that its outer layers have been baked and worn down by cosmic radiation over enormous stretches of time while it drifted through interstellar space. These rays may have sealed much of its inner ice, making it far less easy to evaporate than a normal comet, yet still holding valuable clues about what it was originally made of. This toughness gives it a strong, lasting quality, hinting that it is more likely a piece of a planetesimal than a fragile ball of ice. If 3i Atlas really is a piece of a larger world, then it was probably thrown out of its home star system during the wild early years of planet formation. In young star systems, giant planets often move around, pulling smaller bodies with them. Some fragments are caught into new paths, while others are thrown into deep space. Sometimes the pull of a nearby star adds to the chaos, sending fragments on long interstellar trips that can last for millions upon millions of years. Its path across the sky points toward the constellations of Carina and Scorpius, areas full of star nurseries, where many young stars and planetesimals are born. Maybe 3i Atlas began its life in one of these busy star-forming regions. As it moved through clouds of gas and dust, its path may have been changed slightly, altering its speed and direction just enough to bring it toward our solar system. Though its exact birthplace is still unknown, its path suggests a close link to areas where new stars are being born. To learn more about it, astronomers are studying how reflective its surface is and what chemicals it contains. If its outer layers hold carbon-rich compounds or organic materials, it could mean that it once belonged to a carbon-heavy planetesimal orbiting a larger planet at the edge of its home system. These carbon-rich materials are common in the cold outer parts of planetary systems, where ice, rock, and organic matter mix. Finding them on 3i Atlas would strongly support the idea that we're seeing a tiny leftover from a far larger, long-lost world, a survivor of an ancient planetary system now drifting silently among the stars. When astronomers first saw 3i Atlas, they were immediately faced with an important and interesting question. Was this strange visitor a comet, or was it more like an asteroid? At first, this might seem like a small detail, almost just a difference in naming, but in truth it is very important. Deciding whether an object is a comet or an asteroid changes how scientists understand the making of planets, how space objects change over time, and even how matter moves across the universe. On the surface, comets and asteroids can look quite similar, small dots of light moving across the sky, but underneath, they are very different. Comets are often called dirty snowballs, made of frozen ice mixed with dust and gases that easily turn into vapor when warmed by a star. As these ices melt, they form a glowing cloud of gas and dust called a coma, and sometimes even a long shining tail that stretches across the sky, making them some of the most beautiful sights in space. Asteroids, on the other hand, are drier and harder. They are rocky or metallic bodies that usually stay quiet and unchanged, unless they are hit by something else, or broken apart by space forces. So where does 3i Atlas belong in this cosmic family? At first glance, it seemed more like a comet. When it was found, astronomers saw a faint glow around it, a thin cloud of dust and some weak gas release, showing that frozen ices on its surface were slowly turning into gas. But unlike famous comets such as Comet Borisov, which shone brightly through the solar system with long glowing tails, 3i Atlas acted oddly. Its activity was weak, uneven, and hard to predict, leading some scientists to wonder if it really should be called a comet at all. The mystery deepened when astronomers studied the light it reflected. Using spectroscopy, a method of looking at an object's light to find its chemical fingerprints, they found clear signs of water ice and carbon monoxide, typical materials of comets. This meant that, even if 3i Atlas was not acting like most comets, it still had comet-like parts. The weak gas release might have come from small icy patches on its surface, slowly warming as sunlight reached them, gently letting gas and dust drift into space. But another puzzle appeared. If 3I Atlas was a comet, why didn't it grow brighter or more active as it came closer to the Sun, like most comets do? One idea is that it simply didn't have much easily melting ice. Another is that its surface had become hardened by cosmic radiation and the tough conditions of deep space during its incredibly long trip between the stars. This protective crust could have sealed in its ices, stopping them from melting easily. Then there was its path. Most comets follow long oval-shaped orbits around the Sun, moving close to our star and then travelling far away to the outer parts of the solar system, sometimes repeating this for millions of years. 3I Atlas, however, was different. It followed a hyperbolic path, which means it wasn't held by the Sun's gravity at all. It was on a one-time trip, rushing through our solar system before disappearing forever into the vast emptiness of space. This unusual path was another clue that 3I Atlas was not an ordinary comet. Regular comets usually come from icy areas like the Kuiper Belt, beyond Neptune's orbit, or the faraway Oort cloud, a huge shell that may surround the solar system. Asteroids, on the other hand, are often found in safer zones such as the asteroid belt between Mars and Jupiter, or sometimes in the Kuiper Belt. But 3I Atlas came from neither. It wasn't a long-time member of our solar system. It was an interstellar traveller, a wanderer moving between the stars. Its surface makeup added even more mystery. Asteroids are mostly rocky, filled with silicate minerals and metals, sometimes with small amounts of carbon. Comets are fragile mixes of ice, carbon compounds, dust and organic materials, which often turn to gas when they come near a star. 3I Atlas seemed to have both. It had water ice and carbon monoxide like a comet, but also mineral dust more like an asteroid. All these strange and mixed traits led astronomers to a tempting idea. 3I Atlas might not belong fully to either group. It could be a cosmic mix, a mysterious in-between object, part comet and part asteroid. This idea makes 3I Atlas even more interesting. Maybe it began as a comet in another star system, only to be changed over billions of years of radiation and space travel, giving it the mixed nature we see today. People all around the world are deeply curious about the long and lonely journey of 3I Atlas, its trip from its unknown home system far away among the stars to its short visit to our solar system. People want to know everything: what it is made of, how it travelled across the galaxy, and most of all, how it managed to survive the deadly emptiness of the space between stars. That space between stars is one of the harshest places possible. It is filled with radiation, hit by cosmic rays, and frozen to temperatures hundreds of degrees below zero. To make things worse, space is almost completely empty. In such a place, most fragile objects would quickly fall apart, their surfaces worn away by endless storms of high-energy particles. Yet somehow, 3I Atlas survived. Against all odds, it travelled through the galaxy's cold and dangerous emptiness and entered our solar system still mostly whole. To understand how this strange traveller made it through such a risky and unbelievably long journey, scientists use what are called thermal models. These are powerful computer programs that try to guess how an object like 3I Atlas reacts to heat, radiation and space weather, as it drifts for millions or billions of years between the stars. One of the biggest dangers for such objects is cosmic radiation. As 3I Atlas moved through interstellar space, it would have been constantly struck by invisible bullets, high-energy particles coming from all directions at almost the speed of light. These cosmic rays are mostly made of charged particles, protons, electrons, and even atom cores. Though tiny, when they hit a surface again and again for ages, they can change its chemistry, wear it down, and leave long-lasting marks. For 3I Atlas, this endless bombardment probably darkened and hardened its surface. The constant hits could have melted some of its ice and changed simple molecules into more complex organic materials. Over countless years, this would have created a dark, radiation-baked crust, a tough outer shell that scientists believe now covers the object. Strangely, this damage may have helped protect it. By forming a hard layer on the outside, the crust could have shielded the soft ices and other delicate materials underneath, keeping them safe from being destroyed too soon by the harsh space environment. The survival of 3I Atlas depended a lot on keeping a balance of heat during its endless drift through space. Far from any star, temperatures dropped to extreme lows, hundreds of degrees colder than the coldest places on Earth. In these freezing conditions, water ice, frozen carbon monoxide and other easy-to-change materials stay locked as solids. This deep freeze acted like a natural freezer, keeping the original materials of the object safe for countless ages. But when such an interstellar traveler finally nears a star, everything changes. The star's warmth begins to melt the surface, and those frozen materials start to turn directly into gas. For 3I Atlas, the sunlight it got near our sun was enough to cause a small amount of melting. That is why it showed a faint ghostly glow and a thin trail of dust as it passed through the inner solar system. Thermal models also show that objects like 3I Atlas go through something called thermal shock when they warm up suddenly. Imagine an object frozen for millions or billions of years suddenly exposed to the heat of a star. Its surface would warm up too fast, cracking and breaking under the stress. For 3I Atlas, this sudden heat may explain why it showed only weak activity, just a thin release of gas and dust. Its thick crust likely worked like insulation, keeping most of the ices below from melting while allowing only small amounts to escape into space. Another thing scientists think about is how evenly an object heats up. Because 3I Atlas is small and oddly shaped, it would not warm evenly like a big round comet. Some parts of its surface would absorb more sunlight than others, causing bursts of gas in certain spots rather than a large balanced tail like a typical comet. This uneven activity may explain why 3I Atlas looked so faint and quiet compared to comets like Comet Borisov, which had a brighter and more familiar tail during its journey. Cosmic rays also shaped the heat history of this wandering visitor. Over millions or billions of years, these high-energy particles acted like invisible sculptors, slowly wearing down its outer layers and forming the dark, radiation-processed crust we see today. Beneath that protective shell, the more delicate materials stayed safely preserved, like secrets locked inside a vault, waiting until 3I Atlas finally passed near our sun and revealed part of its story. In the strange and fascinating case of 3I Atlas, scientists think its outer layer, full of organic material, may have worked like a protective shield. This dark crust covered and guarded the fragile, easily melted ices buried deep inside. Without this layer, the ices would have evaporated quickly as the object drifted through the vast emptiness of interstellar space, constantly hit by radiation and cosmic rays. Instead, the shield slowed the process, letting 3I Atlas survive its long, lonely journey between stars. A particularly interesting mystery is what happened to its organic matter during this trip through space. Cosmic radiation can change molecules, sometimes creating new and more complex ones. On the surfaces of comets and small planetary bodies, for example, radiation can form carbon dioxide and other complicated chemicals. The fact that molecules like these may exist on 3I Atlas supports a bold idea, that objects moving between stars could carry pre-life chemicals, spreading the seeds of life across the galaxy. Perhaps 3I Atlas picked up extra organics, similar to those on comets during its travels. If so, it may have been one of nature's messengers, quietly carrying the building blocks of life far from its original home. But much is still unknown. Did these delicate organic compounds survive the extreme cold of deep space? Or did they break down over time? Some scientists suggest that the icy shell of 3I Atlas acted like a freezer, keeping them safe, while others are more cautious. The object's path through our solar system also tells an interesting story. Unlike ordinary comets, which orbit the sun repeatedly, 3I Atlas followed a hyperbolic path, meaning it was just passing through at incredible speed. Its time near the sun was very short. It never stayed long enough to heat up strongly or erupt like normal comets. Instead, it released only faint streams of gas and dust, a quiet traveller rushing onward, untouched by the changes usually seen in icy visitors from the outer solar system. Another big mystery is whether 3I Atlas passed through other star systems before reaching us. Since it came from deep interstellar space, it is very unlikely that its journey was a straight shot from one place to our solar system. Instead, it must have drifted through the Milky Way for millions or billions of years, moving through stellar neighborhoods, passing young stars, and perhaps even being pulled this way and that by invisible gravitational forces. Astronomers know that interstellar objects often form when planets move in young solar systems. The shifting of giant planets can fling comets and small planetary bodies outward, sending them into the galaxy to wander freely. Once ejected, they follow paths that no star can hold, hyperbolic orbits that take them from system to system. 3I Atlas is one of these cosmic wanderers, and its path shows it will never return. It was a visitor, not a resident. When scientists trace its orbit backward, They find it points toward a part of space near the constellations Carina and Scorpius. These star nurseries are crowded with newborn stars and intense activity. It is tempting to imagine that 3I Atlas may once have drifted among them, perhaps nudged onto its path by the gravity of a massive young star. Yet the galaxy is huge, and while simulations suggest possibilities, it is nearly impossible to say for sure which stars it passed. Still, its long journey could not have been uneventful. Interstellar space is not completely empty. It is filled with molecular clouds, cosmic dust, high-energy radiation, and debris from ancient supernovae. As 3I Atlas moved through this wilderness, each encounter must have left faint marks. Its surface likely carries the signs of cosmic weathering. Chemical changes, dust impacts, radiation burns. These cosmic fingerprints may one day help scientists retrace its path, showing whether it once passed another star system. Even if the chance of directly passing through a star system is low, models show that many interstellar objects do drift across multiple stellar regions over long times. So while 3I Atlas may not have come close to other stars, it almost certainly passed through star-forming clouds and dense stellar neighborhoods that slowly changed its surface. Today, what makes 3I Atlas so valuable to scientists is that its outer skin still holds clues to this long history. Its faint activity and thin dust halo hint at a mix of ices and organics changed over countless ages. By studying these changes, researchers may learn not only how it survived its journey, but also whether it carried traces of other worlds on its surface. Tiny hints of chemistry formed in distant star nurseries, and that is why 3I Atlas matters even for planetary defense. Every interstellar visitor gives us more knowledge about the kinds of objects moving through the galaxy. By studying them, we learn how to recognize them, track their paths, and understand what they are made of. One day, this knowledge may help us prepare if a less harmless visitor comes speeding our way. 3I Atlas is like a mysterious traveler from beyond the stars, a rare visitor that briefly passed through our solar system before continuing its endless journey. Its short visit was more than just a curious astronomical event. It carried valuable lessons for how we might protect our planet in the future. Even though 3I Atlas never posed a direct threat to Earth, its sudden arrival reminded us of potential dangers that could arise as we continue discovering more wandering objects, not only in our solar system, but also from the vast spaces between the stars. By studying 3I Atlas, its unusual speed, its strange stretched-out shape, its faint activity, and its fast path through space, scientists realized they could improve early warning systems, create better ways to spot cosmic threats, and plan ways to deal with them if one ever headed toward Earth. Until now, most efforts to protect our planet from space dangers have focused on what astronomers call near-Earth objects, often shortened to NEOs. These are comets and asteroids that move in orbits inside our solar system and sometimes come close enough to Earth to be a concern. Over the last few decades, scientists have become much better at finding these objects and predicting their movements. But interstellar visitors, like the mysterious traveler 3I Atlas, present a whole new set of challenges. Unlike NEOs, these objects come from far beyond our solar system, moving much faster, and they give us very little time to prepare if they happen to be on a dangerous path. One of the biggest challenges is speed. Most ordinary comets and asteroids travel at around 20 to 30 kilometers per second. Interstellar objects, however, can be much faster. 3I Atlas, for example, was rushing toward the Sun at nearly 60 kilometers per second, roughly twice the speed of a typical solar system comet. Because of this incredible speed, it was much harder to spot early. Once it appeared, astronomers had only a short window to track its path and figure out whether it might be a threat. The unusual path of 3I Atlas, its hyperbolic orbit, made it clear that this object was only passing through our solar system. Unlike regular comets and asteroids, which loop around the Sun in repeating paths, 3I Atlas followed an open-ended trajectory, destined never to return. This meant there was no immediate threat to Earth. Yet, its brief visit also served as a reminder of the danger such objects could pose. If another fast-moving interstellar object were ever headed straight for our planet, humanity would have very little time to react. A collision could happen almost without warning, leaving us with few options, whether trying to push the object off course or, in the worst case, evacuating areas most at risk. Detecting objects like 3I Atlas is another major challenge. These interstellar visitors are often small, faint and quiet, giving off very little gas or dust. They can easily blend into the crowded background of stars, making them nearly invisible to most of our current telescopes. Some may already be slipping through our solar system unnoticed, especially if their paths take them far from Earth or through parts of the sky we do not regularly monitor. Large sky surveys, such as the Asteroid Terrestrial Impact Last Alert System, ATLAS, and the Panoramic Survey Telescope and Rapid Response System, PanSTARRS, have greatly improved our ability to find asteroids that come close to Earth. However, they were not designed to detect faint, fast-moving interstellar objects. In fact, 3i ATLAS was only discovered after it had passed its closest point to the Sun. This delayed discovery highlights the urgent need for more sensitive telescopes and new ways to search the skies so that we can spot these visitors earlier. Our strategies for defending the planet must also change. Current methods, like sending a spacecraft to crash into a dangerous asteroid to nudge it off course, called the kinetic impactor technique, or even using nuclear explosions, were designed for slower objects within our solar system. Interstellar visitors, moving at extreme speeds, could make these techniques ineffective. Protecting Earth might require entirely new types of spacecraft, advanced engines, or completely different approaches to planetary defense. Studying details such as the size, shape, and internal strength of objects like 3i ATLAS is essential. Every piece of information helps scientists improve defense plans and prepares us for the types of cosmic visitors we might face in the future. These studies also teach us more about space weather, the flow of cosmic dust, ice particles, and even organic molecules that sometimes travel alongside these objects. Some of this material may even contain fragments of distant planets, carrying chemical clues about how matter behaves around other stars. In this way, learning about interstellar wanderers not only helps protect our planet, but also gives us a rare glimpse into the building blocks of life across the galaxy. Here's a fully rephrased, simplified, and more elaborate version of your text, keeping it vivid, engaging, and with all figures and dates written out in words. The discovery of 3i ATLAS felt like a brand new door swinging open into the unknown, a gateway that invited humanity to imagine what the future of space exploration might hold. For the very first time, astronomers began to seriously consider a daring, almost science fiction idea. What if we could send a spacecraft to meet a visitor from another star system as it raced through our own? The thought was electrifying, sparking visions of a day when humans might finally reach out to touch something that had travelled across the galaxy. Unfortunately, 3i ATLAS's visit was far too brief. By the time we noticed it, the mysterious traveller was already slipping away, too fast for us to launch any mission in time. Yet even in its short passage, it planted a seed of curiosity and wonder in the minds of scientists, engineers, and dreamers alike. Its fleeting presence made us look to the future, toward the day when we might capture or follow such interstellar wanderers, sending robotic scouts to uncover the secrets they carry from distant star systems. The idea of chasing a visitor from beyond our sun is thrilling, but it is also one of the greatest challenges humanity has ever faced in space exploration. To succeed, we would need technology more advanced than anything we have built, new ways to move through space, and carefully timed plans to intercept objects hurtling across the cosmos at unimaginable speeds. The first and most obvious challenge is speed. When 3i ATLAS streaked through our skies, it travelled at roughly 60 kilometers every single second. To put that in perspective, most of our spacecraft moving around the Sun travel at only 10 to 20 kilometers per second. To reach an interstellar visitor, we would need spacecraft capable of matching, or exceeding, those extraordinary speeds. But moving fast is not enough. To intercept a runaway object, a spacecraft must also follow the right path, adjusting its trajectory so it intersects the visitor's route. One clever trick for this is called a gravity assist, or slingshot maneuver. By flying close to a massive planet such as Jupiter or Saturn, a spacecraft can use the planet's enormous gravity to fling itself forward, gaining speed without burning more fuel. This technique helped legendary missions like Voyager, Galileo, and Cassini travel farther and faster than ever before. Even so, for an object as swift as 3i ATLAS, even the strongest slingshot might not be enough. Consider NASA's Parker Solar Probe, one of the fastest spacecraft ever built by humans. Designed to skim close to the Sun, It can reach speeds of around 700,000 kilometers in a single hour. That is incredible. Yet even it would be too slow to catch an interstellar wanderer. Clearly we will need something far faster than today's record-breaking machines. One promising idea is the solar sail. Imagine an enormous, nearly weightless mirror spread out across space. Instead of catching wind like a sailing ship, it catches sunlight. Every tiny particle of light, called a photon, pushes the sail ever so slightly. At first, the nudge is almost imperceptible, but over months and years it adds up, accelerating the spacecraft to incredible speeds without burning a single drop of fuel. With such a sail, we could one day chase a visitor from another star system across the galaxy. This is no longer just a dream. Projects like Breakthrough Starshot already envision fleets of tiny spacecraft equipped with sails, powered not only by sunlight but also by Earth-based lasers. These miniature explorers could potentially reach 1/5 the speed of light, fast enough to reach nearby stars within a human lifetime. Adapted for interstellar visitors, this technology could allow us to pursue objects like 3I Atlas when they appear in our solar neighborhood. Another option is ion propulsion. Unlike chemical rockets that roar with fire and smoke, ion engines move with a gentle, continuous push. They take atoms of xenon gas, charge them, and shoot them out at tremendous speed. The thrust is faint like the weight of a feather on your hand, but it never stops. Over months and years, the spacecraft steadily gains speed, eventually travelling faster than most chemical rockets ever could. NASA's Dawn mission, which visited the asteroid Vesta and the dwarf planet Ceres, demonstrated the quiet but powerful potential of this technology. Stronger ion drives in the future could allow us to chase interstellar travelers, though such missions could take many long years. Timing is just as important as speed. By the time astronomers first spotted 3I Atlas, it was already moving past us too quickly for any spacecraft to reach it. The lesson is clear. To pursue the next visitor, we must detect it early. Fortunately, new telescopes, such as the Vera Rubin Observatory set to open soon, will give us sharper eyes and faster warnings. Early detection could give us the precious time needed to prepare and launch a mission before the object disappears forever. Endurance is another challenge. Interstellar visitors are visible in the inner solar system for only a few short months, yet any spacecraft chasing them might need to travel for years, possibly decades. It would face harsh radiation, constant bombardment from tiny space debris, and the freezing emptiness of the void. Future spacecraft will need stronger materials, smarter systems, and designs that can survive far longer than anything we currently build. If we can overcome all these obstacles, the rewards would be extraordinary. Each interstellar traveler carries priceless clues about how stars are born, how planets scatter, and the hidden rhythms of our Milky Way. Their paths tell us about the movement of gas, dust, and starlight across the galaxy. Everyone is a messenger from the wider universe, bringing whispers of far-off worlds. 3. Atlas's brief visit is not just about studying a mysterious traveler, it is also a rare chance to understand how our galaxy works. By carefully tracking its path, astronomers can learn how objects from other star systems travel, how the Milky Way's gravity shapes their journeys, and how stars and galaxies influence each other across vast distances. Most objects in our solar system, planets, asteroids, and comets, follow closed loops around the Sun. 3I Atlas was different. It travelled along a one-way parabolic path never to return. The Sun's gravity could not hold it, making every moment we observed it precious, because once it was gone, it would be gone forever. By studying its speed and trajectory, astronomers can test ideas about how stars move, how galaxies interact, and how forces in space guide the endless flow of objects between stars. One of the first lessons from 3I Atlas is how the motion of distant stars can fling objects into interstellar space. Its path suggests it may have originated near the constellations of Carina and Scorpius, regions full of young, newly forming stars. Perhaps it was once part of a young planetary system, only to be hurled into the void by the gravitational pull of neighbouring stars, skipping across the galaxy like a stone across water. The discovery of 3I Atlas was an extraordinary moment in human history, almost like stepping through a brand new doorway into the unknown. It opened our eyes to a future where space exploration could reach far beyond our own solar system. For the very first time, astronomers seriously began to imagine the bold idea of sending a spacecraft to follow and study objects that come from other star systems as they pass through our cosmic neighbourhood. Unfortunately, the visit of 3I Atlas through our solar system was far too brief for anyone to mount a mission in time. Its passage lasted only a short while, just a few months in human terms, yet it sparked wonder and curiosity in the minds of scientists, engineers, and dreamers everywhere. It made us start thinking about the future, the day when humans might finally have the tools to intercept these interstellar travelers, or at least send robotic scouts to follow them and uncover the secrets they bring from faraway stars. The idea of sending a spacecraft to meet a visitor from beyond our sun is thrilling, but it is also one of the most difficult challenges humanity has ever faced in space exploration. To make it work, we would need not only the most advanced technology ever invented, but also completely new ways to propel spacecraft and carefully planned missions to chase objects moving at unimaginable speeds. The first major challenge is speed. When 3I Atlas shot through our skies, it was travelling at about 60 kilometers every single second. To put that in perspective, that is much faster than any human-made spacecraft has ever gone. Most spacecraft that explore our solar system move at only about 10 to 20 kilometers per second. This means that if we ever want to catch an interstellar visitor, our spacecraft will need engines capable of matching or even exceeding these incredible speeds. But moving fast is only part of the problem. A spacecraft must also carefully adjust its path through the solar system so it meets the visitor at exactly the right place and time. One way to do this is by using gravity assists, sometimes called slingshot maneuvers. By flying close to giant planets like Jupiter or Saturn, a spacecraft can use their enormous gravitational pull to boost its speed, gaining momentum without carrying massive amounts of fuel. This technique helped legendary missions such as Voyager, Galileo, and Cassini explore the outer solar system. Yet even with these boosts, keeping up with something as fast as 3I Atlas is an enormous challenge. Consider NASA's Parker Solar Probe, one of the fastest machines humans have ever built. It was designed to fly very close to the Sun and can reach speeds of about 700,000 kilometers in a single hour. That is an astonishing number, yet even this champion of speed would still be too slow to catch an interstellar traveler. Clearly, future missions will need technology even more advanced than our current fastest spacecraft. One exciting idea is the solar sail. Imagine a huge, paper-thin mirror stretched out in space. Instead of catching the wind like a sail on a ship, it catches sunlight itself. Each particle of light, called a photon, carries a tiny push. When the photons hit the sail, they slowly push the spacecraft forward. At first, the push is almost invisible, but over months and years it builds up to tremendous speed, all without using a single drop of fuel. With a solar sail, a spacecraft might one day accelerate enough to chase an interstellar traveler across the stars. This idea is no longer just science fiction. Projects like Breakthrough Starshot are already planning to send swarms of tiny spacecraft equipped with these sails. Powerful lasers on Earth would push them even faster, aiming to reach speeds up to 1/5 the speed of light. At that speed, these miniature explorers could reach the nearest stars within a single human lifetime. A system like this could one day be adapted to pursue interstellar visitors as they pass through our solar system. Another possibility is ion propulsion. Unlike chemical rockets, which roar into space with fire and smoke, ion engines move quietly by using electricity. They take atoms of xenon gas, charge them, and shoot them out at very high speeds. The push is very weak at first, like the weight of a feather on your hand, but it never stops. Day by day, year by year, the spacecraft slowly gains speed, eventually surpassing most chemical rockets. NASA's Dawn mission, which explored the asteroid Vesta and the dwarf planet Ceres, showed just how powerful this slow but steady technology can be. Stronger ion engines could one day allow us to catch up with an interstellar traveler, although the journey might take many years. Even with these powerful engines, timing is critical. By the time astronomers first noticed 3I Atlas, it was already speeding past, too late for a spacecraft to be launched. This taught us an important lesson. To chase the next visitor, we must discover it as early as possible. New telescopes, such as the Vera Rubin Observatory, will help us spot these objects sooner, giving humanity a chance to prepare a mission before the traveler disappears back into the darkness. Endurance is another challenge. Interstellar objects are visible in the inner solar system for only a few short months. A spacecraft chasing them, however, might need to travel for years or even decades. It must survive harsh radiation, tiny space debris, and the freezing emptiness of deep space. To do this, we will need stronger materials, smarter onboard systems, and spacecraft capable of lasting far longer than anything built today. If we overcome all these challenges, the rewards will be extraordinary. Each interstellar visitor carries priceless information about the formation of stars, the movement of planets, and hidden patterns in our Milky Way galaxy. Their paths reveal the motions of gas, dust, and starlight across the universe. Every one of these travelers is a messenger from the wider cosmos, carrying whispers of distant worlds. So the big question remains: when the next cosmic wanderer sweeps through our skies, will humanity finally be ready to give chase? 3. Atlas's short visit to our solar system is not just about learning what this strange traveller is made of. It is also a rare chance to see how our galaxy itself works. By carefully watching its movement, astronomers can uncover secrets about how objects from other star systems travel, how the Milky Way's gravity shapes their paths, and even how stars and galaxies affect each other during their long trips through space. Most objects in our solar system, like planets, asteroids, and comets, follow closed round or oval paths around the Sun because of the Sun's gravity. 3i Atlas, however, is different. It is not held by the Sun at all. Instead, it moves along what is called a parabolic path, a kind of one-way trip through our part of space. The Sun's pull cannot trap it, so once it passes by, it will keep going outward and never return. That makes every moment of watching it priceless, because once it is gone for good. By checking its speed and drawing its path, astronomers can test important ideas about how stars move, how galaxies affect each other, and how strong forces in space guide the endless flow of objects between the stars. One of the first big lessons 3i Atlas teaches us is how the motion of stars can change the course of wandering interstellar travelers. Its path shows that it may have come from a far-off area near the constellations of Carina and Scorpius, places full of young stars that are still forming. Perhaps 3i Atlas was once part of a new planetary system there, until the pull of nearby stars threw it out into deep space, like a stone skipping across water. When scientists trace its path backward in time, they see how close encounters with giant stars or huge clouds of gas and dust could have bent its orbit, sending it on this fast and hard-to-predict journey. This helps them understand how such visitors are spread across the Milky Way and why some of them pass near Earth. Its very high speed suggests that it may have come from the far edges of the galaxy, where stars are fewer and more spread out. By comparing its motion with computer tests of how stars drift and change position, astronomers can check and improve their ideas about how the Milky Way has grown and changed over billions of years. If future telescopes find more travelers like 3i Atlas, scientists will be able to build an even clearer picture. They will see how these objects are thrown out of their home systems, how they are shaped by the gravity of nearby stars and giant clouds, and how they later become lonely wanderers across the galaxy. 3i Atlas also reminds us that the Milky Way is not a still or quiet place. It is alive and always moving. Stars circle the galactic center, clouds of gas move and crash, and even the unseen dark matter has its role. Every pull of gravity between stars or planets can upset the balance of a system, sometimes pushing out whole worlds or comet-like objects into the wide interstellar space. 3i Atlas may itself be the result of such ancient unrest, perhaps moved by the passing of a nearby star, or by moving clouds of dust and gas that changed its course. Studying objects like this also brings us closer to the story of how our galaxy was born and changed over time. Most worlds, planets, moons, asteroids, and comets stay tied to stars. But the fact that some can be flung into empty space shows us that the Milky Way has always been unsettled. Long ago, when stars were still forming and young planetary systems were unstable, countless bodies may have been thrown out into space. 3i Atlas is living proof of that history, like a fossil floating between the stars. As astronomers tracked its speed and direction through our solar system, they also measured how it reacted to the Sun's pull. Its quick passage showed that it came from a part of the galaxy where gravity is weak, far away from large star groups or powerful stellar systems. That makes it especially useful for testing how the galaxy's gravity shapes wandering travelers. Each close study helps improve models of how stars move and how the Milky Way itself flows through the universe. On an even bigger scale, 3i Atlas helps us learn about the unseen matter that fills the spaces between stars. As it glided through our solar system, scientists carefully watched how it reacted to cosmic radiation, interstellar gas, and the solar wind. These small effects can show how thick the material between stars is, helping us build a kind of map of the Milky Way's hidden web of gas and dust. Step by step, travellers like 3i Atlas let us uncover the conditions of the galactic sea, the vast space in which all stars float. One of the most interesting puzzles about 3i Atlas is whether it left behind any cosmic crumbs as it rushed through our solar system. 3i Atlas is not from our neighbourhood. It is a traveller from another star system far beyond our Sun. While it may have mostly stayed whole during its short visit, its great speed could have shaken off tiny bits of material, micrometeorites and dust grains, that drifted away from its surface. Some of these tiny pieces may have floated into the empty space of our solar system, while others might have fallen into Earth's air, burning up as faint streaks of light too small for the human eye to see. If so, those pieces have now become part of the wide cloud of cosmic dust that surrounds and stretches far beyond our solar system. Studying how such travellers interact with the places they pass through is one of the most exciting challenges for astronomers. As 3i Atlas moved closer to the Sun, it faced stronger bursts of solar energy. This heating likely made some of its outer layer weaken and peel away. Ices inside its crust, ices made of water, carbon dioxide, or perhaps stranger frozen chemicals, would have turned directly into gas. Along with them, dust and tiny rocky grains would have been released into space, forming a faint tail behind it. These micrometeorites, no bigger than grains of sand, are the cosmic crumbs left behind by such travellers. But 3i Atlas's trip was not easy. Speeding through space at such high speed meant it was constantly hit by harsh forces, intense sunlight, scorching heat near the Sun, and the unseen but strong strike of cosmic rays. All of these slowly wore away at its surface, breaking off small bits and scattering them into space. Even if only a little dust was lost, those particles could have joined the interstellar cloud of dust drifting through our solar system. Although these pieces are far too small to see without strong instruments, they are very important. Space missions from NASA and other groups have shown that cosmic dust is not just leftover debris. It helps build planets, moons, and other worlds. Even the smallest dust grains that fall into Earth's air tell us stories about where they came from, carrying chemical clues that reveal their origin. If 3i Atlas really did shed dust, it might even have added, in a tiny way, to the streams of particles that cause Earth's meteor showers. Each year in the month of August, for example, our planet passes through the remains of Comet Swift-Tuttle, creating the well-known Perseid meteor shower. If 3i Atlas left a similar path of dust and rock, Earth could, in theory, one day cross it. However, because 3i Atlas moved through so quickly, it is unlikely that it left behind enough material to change any of our yearly meteor showers. Still, looking at 3i Atlas and comparing it to other interstellar visitors gives us hints. Comets like Borisov, for example, have been seen releasing large amounts of dust and gas as they pass through the inner solar system. Since 3i Atlas was probably also made of ice, it likely released at least some dust. Though less than comets we know well, that means its gift to the cloud of interstellar dust in our solar system was small but not zero. Even a small gift, however, is meaningful. Every tiny grain of dust left behind by such travellers gives scientists a rare sample of material from faraway star systems. By studying these traces, astronomers hope to uncover secrets about how planets are born in other systems and about the chemistry of the space between stars, the interstellar medium. Some dust grains may even hold organic molecules, the simple building blocks that can one day lead to life. This is why the path of 3i Atlas matters so much. Each interstellar traveller we find is a clue to a much bigger puzzle. How many of these cosmic wanderers are out there, how often they pass through our solar system, and what they can teach us about the galaxy beyond our Sun. 3i Atlas may have come and gone in a short time, but the mysteries it left behind could help us understand not just a single strange visitor, but the whole hidden crowd of interstellar travellers moving through the Milky Way. The brief but unforgettable journey of 3i Atlas through our solar system has opened up exciting new questions about what kinds of strange travellers might be drifting across the vast spaces between the stars. 3i Atlas is only the second confirmed visitor from beyond our solar system, appearing after the first strange interstellar wanderer, Oumuamua, which was discovered in the year 2017. These two travelers, so different yet equally strange, have given humanity rare and valuable glimpses into a hidden side of the universe, the way objects move freely between the stars, carrying with them secrets of distant worlds. By carefully studying the path of 3I Atlas, astronomers are beginning to piece together a larger story. They are asking how often such visitors appear, where they might have been born, and what happens when they sweep through a new star system for only a short time before vanishing again into the dark. The very fact that scientists managed to detect 3I Atlas at all is amazing. It was racing through space at incredible speed, with only a small window of time to be seen. Its discovery, together with that of Oumuamua, suggests something important. Interstellar objects may not be as rare as people once thought. Instead, there could be many more of them slipping silently through our skies, hidden by their short visits and fast movements. 3I Atlas was only visible for a few months before it vanished again into the deep darkness of interstellar space. Its brief appearance is a striking reminder that countless other cosmic wanderers could already be gliding through our solar system right now, completely invisible to us. Luckily, sky surveys like the Atlas program and Pan-STARRS are constantly improving, giving astronomers better and sharper tools to spot these fast-moving visitors. Still, the true number of interstellar objects drifting through the Milky Way remains hidden, a vast and thrilling mystery. In this sense, 3I Atlas might have been just the tip of a massive cosmic iceberg, hinting at a much larger population of unseen travelers silently roaming our galaxy. If this idea is correct, then interstellar visitors could actually be quite common. Many of them may be fragments of ancient star systems, broken off pieces of planets, icy comets, or rocky asteroids. Over billions of years, the gravitational pull of giant planets or close encounters with other stars could have flung these objects into the endless void of interstellar space. Once released, they drift endlessly between stars, sometimes by chance entering the gravitational reach of a new system, just as 3I Atlas briefly did when it passed near our Sun. Every discovery like this is more than just exciting. Each sighting brings scientists closer to solving some of the biggest cosmic mysteries. With enough observations, astronomers could one day estimate how many interstellar objects truly wander through the Milky Way. They could also figure out how often these hidden visitors sneak into our solar system. Even more importantly, each observation helps refine our understanding of gravity on the scale of the galaxy, showing how the Sun, planets, and distant stars tug on these wandering objects and bend their paths as they travel through space. 3I Atlas's unusually high speed adds another fascinating layer to its story. Unlike ordinary comets and asteroids that belong to our solar system, this visitor was moving much faster, hinting that it likely originated in the distant reaches of the galaxy, where the pull of gravity is much weaker. This supports the idea that many interstellar travelers are born on the outer edges of star systems and are then flung into deep space after encounters with massive planets or near collisions with their parent stars. Perhaps the most captivating aspect of 3I Atlas is what its path has taught astronomers about how these objects interact with our solar system. Because they move so quickly, interstellar visitors are far more difficult to study than local comets, which return again and again in long, predictable orbits around the Sun. Interstellar objects, in contrast, give scientists only a single opportunity to observe them as they streak past. Yet even in those fleeting moments, they reveal priceless information about how gravity twists their courses, how they behave near the Sun, and how they might one day cross paths with planets or other small bodies in their journey through the galaxy. When 3I Atlas burst into our solar system from the far reaches of interstellar space, astronomers around the world found themselves facing a question that seemed almost like science fiction. Could this mysterious visitor survive the immense pull of the Sun's gravity without breaking apart? Objects like comets and asteroids that orbit within our solar system are familiar and, to a degree, predictable. Scientists have studied their shapes, compositions, and behaviours for centuries. But something that comes from another star system is completely unknown. Its strength, what it is made of deep inside, and even the way its materials are held together are mysteries. That is why 3I Atlas, hurtling along at breathtaking speeds of tens of kilometres every single second, immediately became a fascinating object of study. Researchers were eager to see how it would react to tidal forces, the stretching and squeezing effects caused by gravity when an object passes near a massive body like the Sun. Tidal forces are not some abstract concept. They are very real. Picture a rope held between two people. If one person pulls harder than the other, the rope stretches unevenly and might even snap. In space, gravity works in a similar way. The side of an object closer to the Sun feels a stronger pull than the far side, creating what scientists call a gravitational gradient. This difference in pull stretches the object along its length. If the object is weak, loosely packed, or oddly shaped, this stretching can produce cracks, knock pieces off, or, in extreme cases, tear the object completely apart. Astronomers have seen this happen many times. Comets that pass too close to the Sun can split spectacularly, and even asteroids can fracture when they approach large planets. When 3I Atlas entered our solar system, there was a real concern that it might meet the same fate. The Sun's gravity could have easily turned it into a cloud of drifting fragments. Yet, as scientists continued their observations, they noticed something remarkable. 3I Atlas stayed intact. Unlike many comets that form long, glowing tails of gas and dust when warmed by the Sun, this visitor barely showed any activity. Its response was faint, almost silent, indicating that its structure was solid and tightly bound. Instead of being made mostly of fragile, easily evaporating ice, its body seemed to be a tougher combination of rock and ice, capable of resisting the Sun's intense heat and the stretching effects of gravity. For astronomers, this was a golden opportunity. Here was the first real chance to observe how a true interstellar object behaves when stressed by the Sun's gravity. The fact that 3I Atlas held together offered new insights into the nature of such travelers. It showed that not all interstellar visitors are fragile snowballs doomed to crumble. Some are strong, resilient wanderers, capable of travelling across the galaxy and passing through other solar systems without falling apart. This realization raised an even bigger question. If 3I Atlas could survive the Sun's pull mostly unharmed, how many more of these travellers might enter our solar system in the future? Were we ready to spot them, study them, and perhaps even send missions to meet them? Fortunately, modern astronomy is starting to make this possible. Telescopes like the Panoramic Survey Telescope and Rapid Response System, PAN-STARRS for short, and the Asteroid Terrestrial Impact Last Alert System, or ATLAS, scan the skies every night for fast-moving objects. These observatories are designed to catch things that are small, faint, or moving so quickly that they might otherwise go unnoticed. Soon, even more powerful instruments will join the hunt. The Vera-C, Rubin Observatory, with its Large Synoptic Survey Telescope program, will watch the sky in incredible detail every single night, giving scientists the ability to detect interstellar objects earlier and track their paths with extreme precision. Early detection is crucial because interstellar objects move at astonishing speeds. 3I Atlas, for instance, was travelling so fast that conventional spacecraft would have no hope of catching up. To study such visitors, scientists will need advanced technologies, ion drives that push spacecraft forward with streams of charged particles, or enormous solar sails that use the pressure of sunlight to glide across space. With these tools, robotic probes could one day chase these interstellar travellers, study them closely, and even collect samples of their material. The importance of this cannot be overstated. Objects like 3I Atlas are more than just unusual rocks. They are frozen messengers carrying chemical histories from distant stars. Their composition could reveal how planets form around other stars, what kinds of molecules are common in other systems, and even whether the basic building blocks of life exist throughout the galaxy. Imagine the discovery if one of these objects contained complex carbon-based molecules, the essential ingredients of life. That would suggest that life's building blocks may not be limited to Earth, but could travel between stars, carried across the galaxy on ancient cosmic travellers. 3I Atlas was only the second confirmed interstellar object ever observed in our solar system, the first being the mysterious Oumuamua in the year 2017. Like its predecessor, it provided scientists with priceless clues about the variety of objects roaming through the Milky Way. Its unusual lack of a bright tail showed that not all visitors behave like the comets we know. Some are tougher, more secretive, and possibly far older than anything we have seen before. The sudden appearance of 3I Atlas served as a powerful reminder to humanity of an important challenge: being prepared. Even though the chance of one of these strange visitors actually hitting Earth is extremely low, their incredible speed makes them very hard to track and study. Being ready for future encounters is not just about satisfying our curiosity, it is a responsibility for science. By running computer simulations, planning careful strategies, and improving our observational techniques now, astronomers can ensure that when the next interstellar traveler arrives, we will be ready to study it thoroughly, without missing a single opportunity. And what a treasure those studies could be. Each of these objects carries a story that is completely unique, depending on where it came from. Some may have formed in young, violent star systems, where planets are still being built and stars are full of raw energy. Others may have spent billions of years drifting alone through the freezing darkness of interstellar space, preserving ancient material that has never been disturbed since the birth of their original star. Studying them is like opening a window into the earliest history of the galaxy, exploring places we could never reach on our own. The future of studying these objects is incredibly exciting. With more powerful telescopes, faster ways to detect them, and spacecraft that can travel farther and more efficiently, the day is approaching when we will no longer have to rely on luck to meet interstellar visitors. Imagine a mission designed from the start to chase one of these cosmic travelers, to collect samples and bring its hidden secrets back to Earth. Such a mission would not just be another step in our exploration of space, it would mark the beginning of a completely new chapter in human discovery, a chapter in which the stars themselves begin sending us their stories, one visitor at a time. Bringing an object like 3I Atlas, a true wanderer from the vast emptiness between the stars, into the inner reaches of our solar system might sound like a story straight out of a science fiction book. And yet, astronomers have asked this question completely seriously. Could something like this actually happen? The main difficulty comes from the incredible speed at which these interstellar visitors travel. 3I Atlas, for example, was racing through space at nearly 60 kilometers every single second. To give that some context, in just one single minute, it could cross a distance greater than the space between the Earth and the Moon. That is an unimaginable speed, far too fast for the Sun or any of the planets to catch or control. The gravitational pull of our solar system is simply not strong enough to stop or hold on to an object moving this fast. Most interstellar visitors, therefore, follow what scientists call hyperbolic paths, curved routes that let them swing by the Sun and then continue onward, never to return. But could it, at least in theory, be possible to catch an object like 3I Atlas and hold it in orbit around the Sun, the Earth, or even a massive planet like Jupiter or Saturn? The answer is yes, in theory, but doing so would be almost unimaginably difficult. To understand why, we need to focus on two crucial things: speed and energy. Asteroids and comets that were born in our own solar system usually travel in oval-shaped orbits, kept bound tightly by the Sun's gravity. Interstellar objects, by contrast, come from star systems far away and charge through space at speeds much higher than anything native to our Sun's neighbourhood. They are not bound by the Sun's pull, and unless something slows them down, they will not stay. To trap one of them, it would need to lose a huge portion of its kinetic energy, the energy of its motion. This rare process is called gravitational capture, and it happens so infrequently that astronomers can count the examples on one hand. The best-known case is Comet Borisov, discovered in the year 2019. Borisov was the first interstellar comet ever confirmed by astronomers. Yet even Borisov was never truly captured. Its path was also hyperbolic, meaning it arrived, swung past the Sun, and then departed, leaving our solar system forever. So, how could a capture even happen? The most realistic chance would be a close encounter with a giant planet like Jupiter or Saturn. If the interstellar object flew past at exactly the right angle and speed, the planet's immense gravity might slow it enough to loop around, perhaps even settle into a stable orbit around the Sun. But the conditions would have to be nearly perfect, and the odds of such a cosmic coincidence happening naturally are vanishingly small. Even the strong gravity of a gas giant is usually not enough to stop something moving so quickly. Most of the time, these visitors just rush past, untouched. Astronomers have imagined more complex scenarios, though. One idea is a kind of cosmic relay race, where the object passes close to several planets in a specific sequence. Each encounter slows it slightly, like passing a baton, until it could eventually be captured. Spacecraft often use this method, called gravitational assist, to gain or lose speed and change direction. In theory, a similar chain of planetary encounters could slow an interstellar object enough to keep it. but in practice, it would require perfect timing, extraordinary luck, and possibly even help from advanced human technology. Another possibility is that the object might have already slowed down during its journey through the galaxy. Close passes by other stars, planets, or clouds of gas could reduce its speed before it ever reaches our solar system. But even with this, the chances of actual capture remain incredibly small. And yet, even without capturing it, 3i Atlas offered humanity something priceless. It was much more than just a lump of rock and ice. It was a time capsule from another star system. Inside its frozen body were materials that formed around a distant star far beyond our own corner of the Milky Way. Locked within its icy shell were ancient samples of the very building blocks of planets, preserved across billions of years. Studying an object like this is like reading a message sent across the galaxy by another world, delivered to us after eons. Objects like 3i Atlas are often fragments of something larger, pieces of shattered moons, broken planets, or tiny planet-building blocks called planetesimals. Long ago, these fragments were flung out of their home systems by the pull of giant planets or the disruptions of nearby stars. Travelling untouched through the freezing emptiness of interstellar space, they carry a kind of original purity, a window into the early stages of star and planet formation. When astronomers observed 3i Atlas during its brief visit, they found evidence of water ice, carbon monoxide, and other delicate chemicals on its surface. These are substances that typically form in the icy outer regions of star systems. That discovery suggests that 3i Atlas may have come from a distant frozen birthplace, much like the regions where many of our own comets were born. So, while capturing such a visitor may remain nearly impossible, its fleeting passage still gave us an extraordinary gift, a rare look into the chemistry, history, and evolution of a star system beyond our own. When astronomers first spotted this strange traveller, it became immediately clear that it was no ordinary comet. This was not simply a frozen ball of rock and dust drifting silently through space. It was far more remarkable, a cosmic messenger carrying secrets from a time and place so distant that it stretches human imagination to its limits. What makes 3i Atlas so valuable is not just the frozen gases or rocky fragments it carries, it is the story those fragments tell. In a way, it is a message, sealed billions of years ago in a faraway star system and delivered to us across the vast reaches of space. Long before our sun had ever ignited its fiery heart, long before Earth had oceans, mountains, or even a sky, a vast, quiet cloud of gas and dust floated somewhere far across the Milky Way. This enormous molecular cloud was cold and heavy, packed with the raw ingredients of creation: hydrogen, oxygen, carbon, silicates, and tiny frozen molecules that would one day form new stars and planets. Within its vastness, delicate balances of temperature, density, and chemical makeup quietly shaped the things that would emerge from it. Billions of years ago, in such a remote and lonely corner of the galaxy, 3i Atlas was born. Minute grains of dust and wisps of gas slowly clung together, sticking, colliding, and growing until they became a small, solid world. Over time, gravity, chance collisions, and the chaotic movements of its birthplace flung this tiny object far from home, sending it on a journey into the endless dark spaces between the stars. Unlike the asteroids, comets, and moons in our own solar system, many of which have been scorched, battered, and reshaped countless times by the sun's heat and violent collisions, 3i Atlas has spent almost all of its long life untouched. For billions of years it drifted silently through the void, protected from the forces that usually scar or transform space rocks. That is what makes it priceless. Hidden beneath its icy surface are the fingerprints of the cloud in which it formed, preserved exactly as they were when it first came together. By studying this interstellar traveller, astronomers can peer into a chapter of cosmic history far older than anything in our own solar system, a record of a time before the Sun, before Earth, and before the planets we know existed. Imagine holding a sample of water or dust that has remained unchanged since the very beginning of another planetary system. That is what 3i Atlas offers scientists, a direct glimpse into conditions in a system that might have been very different from our own. By examining its surface and interior, researchers can start to trace the chemical steps that shaped it. If simple molecules such as amino acids, the tiny building blocks that eventually form proteins, are found inside, it would suggest that the place where 3i Atlas was born could have supported life. These molecules are the first stepping stones toward living cells, and finding them inside an object from another star system would strongly hint that the galaxy is filled with the basic ingredients for life. Some comets in our own solar system already carry these molecules, but discovering them in a visitor from another star system carries an even deeper meaning. It would suggest that the recipe for life is universal, repeated in many places across the galaxy, and not limited to the planets that circle our Sun. In this sense, 3I Atlas can be seen as a cosmic messenger, carrying the building blocks of life across unimaginable distances. As it drifts from one star system to another, it may quietly scatter seeds of life, leaving behind the chemical foundation on which new living worlds could someday grow. But 3I Atlas may offer even more than just molecules. Its rocky components, such as silicates and metals, show that it may once have been part of a much larger body, perhaps a moon, a planetesimal, or even a fragment from the violent early days of its parent system. If so, then this tiny traveller is not only a messenger, but also a fossil from a destroyed world. Just as fossils on Earth reveal the creatures that lived long ago, 3I Atlas offers scientists a window into the rocks and structures of another solar system. Its dust, minerals and ice could reveal what kinds of planets were forming around its star billions of years ago, whether they were rocky like Earth, icy like Europa, or something completely unlike anything we have seen. This possibility excites astronomers because it widens our understanding of what kinds of worlds may exist throughout the galaxy. By studying one small visitor that happened to wander into our neighbourhood, we may learn about entire planetary systems that would otherwise remain hidden. For planetary scientists, objects like 3I Atlas are nothing less than treasure chests. They provide material that does not belong to our solar system, material formed under conditions we cannot fully recreate or observe anywhere else. Every grain of dust, every bit of ice holds a clue. Together, these clues could help astronomers understand how stars and planets form, evolve, and perhaps even nurture life. By comparing 3I Atlas with the asteroids and comets we already know, scientists can spot patterns and differences. Does it have more carbon than comets in our own solar system? Does it carry strange ices rarely found near the Sun? Are its silicates crystal-like or glassy? Each answer sharpens our understanding not just of 3I Atlas, but of how planets form across the galaxy. Perhaps the most thrilling aspect of 3I Atlas is its connection to the mystery of life itself. For decades, scientists have asked whether life began only once, on Earth, about 4 billion years ago, or whether the building blocks of life are scattered across the universe, ready to take root whenever the conditions are right. 3I Atlas may be a clue to answering that timeless question, bridging the vast emptiness between the stars and the very origin of life. Interstellar objects like 3I Atlas bring new excitement to the age-old question of where life comes from. They hint that the building blocks of life may not be confined to a tiny corner of our Milky Way galaxy. Instead, these ingredients could be scattered across vast distances, carried for billions of years by icy wanderers before landing on young planets ready to host them. This idea is at the heart of the Panspermia Theory. Panspermia suggests that the essential molecules for life, or even tiny forms of life themselves, could travel from one star system to another, planting the seeds of life on new worlds. If 3I Atlas contains amino acids, nucleobases, or other carbon-rich compounds, it would provide strong support for this idea. If that were true, Earth might not be unique at all. Our planet could simply be one of countless worlds that were seeded by these wandering carriers of life. Imagine billions of years ago, long before humans, dinosaurs, or even trees existed, an interstellar object like 3I Atlas collided with the young Earth. As it burned in the atmosphere or melted in the early oceans, it may have delivered molecules that would eventually form DNA and proteins. Without that lucky delivery, Earth might have remained a lifeless rock and water. And if this could happen here, why not elsewhere? How many distant planets, orbiting far-off suns, have been touched by similar travellers? How many alien oceans might have quietly begun the process of life, sparked by molecules brought from afar? The discovery of 3I Atlas is just the beginning. Before this, astronomers had only confirmed two other interstellar objects, Oumuamua, found in the year 2017, and Borisov, discovered in the year 2019. Each new visitor offers fresh insights, new mysteries, and more chances to learn. As telescopes improve and sky surveys become more detailed, Astronomers expect to find many more interstellar travelers. Each will have its own story, some icy comets, some rocky fragments, and some possibly completely unexpected forms. The more of them we study, the clearer our understanding becomes of the incredible variety of star systems across the galaxy. Every discovery brings us closer to answering key questions. How common are planets like Earth? How often do planetary systems form in ways very different from ours? And most importantly, how often do life's seeds take hold? Humans have wondered for thousands of years about the origins of life. Some believe life began naturally on Earth, from simple chemicals in ancient oceans. Others wonder if life's first spark came from far away, carried across the emptiness of space. One of the most intriguing scientific ideas exploring this is panspermia. The word panspermia comes from Greek and means seeds everywhere. In simple terms, it suggests that life's building blocks, or tiny forms of life, could travel from world to world, hitching rides on comets, asteroids, meteors, or interstellar objects from distant stars. This doesn't mean fully formed alien life is zooming across space. Instead, it means that small molecules, powerful in their potential, might be spread across the galaxy, ready to grow into life if conditions are right. For centuries, panspermia was mostly a speculative idea, but with modern astronomy, chemistry, and space exploration, it has become a serious field of study. Scientists now see that the universe might not be as empty as it seems. The dust and ice drifting between stars could be filled with the ingredients needed to spark life. One of the most exciting developments in this field is the discovery of interstellar objects, bodies that did not form in our solar system, but drifted into it from distant parts of the galaxy. The best-known examples are Oumuamua, discovered in the year 2017, and Borisov, found in the year 2019. More recently, 3i Atlas joined this exclusive group. Each of these objects offers a chance to explore whether life's building blocks can really travel across the stars. Astronomers studying 3i Atlas are not just observing a strange rock. These visitors act like messengers from other star systems, carrying hints about worlds light years away. Along their long journeys, they are bombarded by radiation, cosmic rays, and tiny dust particles. Even so, many scientists believe these objects may still preserve valuable materials such as organic molecules or prebiotic compounds. Organic molecules are chemical ingredients made of carbon, hydrogen, oxygen, and nitrogen, the same elements that form all life on Earth. Prebiotic compounds are chemicals that aren't alive but could help start life if conditions are right. Examples include amino acids, which build proteins, and nucleobases, which are essential for DNA and RNA. If interstellar objects like 3i Atlas can carry these molecules across the galaxy, panspermia moves from theory to reality. Life might not be rare and fragile. It could be something the universe naturally spreads, scattering seeds of possibility across the stars. We do not need to look only at distant interstellar objects to understand this. Our own solar system holds clues. Comets, for instance, are icy bodies that usually live far from the Sun in regions like the Kuiper Belt and the Oort cloud. The Kuiper Belt lies just beyond Neptune and contains countless small icy worlds. The Oort cloud is even farther out, forming a vast, distant shell around the solar system. When comets are disturbed, perhaps by a passing star or a planet's gravity, they can fall toward the Sun. As they approach, their ices heat up and release gases, creating the bright tails we see in the night sky. But comets are more than beautiful. They are treasure troves for science. Studies have shown that comets contain complex organic molecules, including simple sugars, alcohols, hydrocarbons, and amino acids. NASA's Stardust mission, launched in the year 2004, flew past Comet Wild 2 and collected dust samples. When scientists analysed these grains on Earth, they found amino acids, the very molecules life uses to build proteins. This was a groundbreaking discovery. It showed that life's building blocks are not unique to Earth. They can form in the cold, dark reaches of space. This suggests that comets, asteroids, and other icy bodies may have bombarded early Earth billions of years ago, delivering the materials needed for life to begin. If comets in our solar system can carry these molecules, then interstellar objects like 3i Atlas, formed long ago around distant stars, could do the same. In fact, they might be even better carriers, preserving ancient materials untouched by heat and radiation. They could act as frozen time capsules, holding chemical fingerprints from the earliest days of star and planet formation. Proving that these objects carry life's building blocks would have huge implications. It would show that life's recipe is not rare or unique to Earth. Instead, it could be a natural process happening across the Milky Way, perhaps in nearly every star system. In this vision, the universe is full of life's ingredients, molecules drifting silently, waiting for a suitable world. On planets or moons with liquid water, warmth, and stable conditions, these molecules could slowly assemble into living systems, evolving over time. When astronomers observed 3I Atlas, they noticed a faint dusty halo surrounding it. Tiny grains released during its journey. This dust may contain organic material, tiny chemical breadcrumbs offering clues about the system where it was born. If interstellar dust is common, it may play a bigger role than we realized in forming new star systems. Clouds of gas and dust that collapse to make new suns and planets could already carry life's ingredients. Young worlds might begin not as barren rocks, but sprinkled with the chemicals needed for life before they are fully formed. The discovery of water ice on 3I Atlas adds to the story. Water is essential for life as we know it. If interstellar objects often carry both water and organic molecules, they could act as delivery ships, bringing life's starter kit to newborn planets across the galaxy. This mirrors what likely happened on Earth. Billions of years ago, our young planet was bombarded by comets and asteroids. These impacts may have brought much of our ocean water and the molecules that eventually gave rise to biology. Similarly, travelers like 3I Atlas may sprinkle distant worlds with ingredients for life. One major question remains: can interstellar objects survive such long journeys intact? Space is dangerous, full of radiation, collisions, and gravitational stresses. Even comets in our solar system sometimes break apart near the Sun,